Ooh, look at all those cool things I can do. Ah. All right. Does anyone have any questions about yesterday?
No, I went back over recording that you did.
Okay.
So
Did it help?
yes, much.
I hope you didn't do the whole thing because you would have been up until like 3 in the morning.
Yeah, no, I didn't do the whole thing. I just
Okay,
skipped through.
So today, by the way, you guys should give yourself a big pat on the back because you've now gone through, even though we're only a little bit halfway through the manual, a little bit more than halfway through the manual, we've done about 2/3 of the material because there's a lot of stuff that, really requires a lot more than just reading in order to understand it. So I'd say today is a little bit easier day, which is good because it's only 4 hours. So let's see, is everyone who's signed up for an exam good to go?
As far as I know, I think so.
Okay, and I noticed that Victoria and Natalie's mom is signed up, but Victoria and Natalie aren't, correct?
Correct. We
Okay.
realized we had some issues we would have to work through as far as enough cameras for everybody.
Mm-hmm. Well, actually, we can't give everybody a test at the same time. So you guys can do them serially. You can do, you finish and someone else and someone else. So if you want to do that, that's how we do it, because we don't have enough people to test everybody at once either.
I'd like more time to study before I take the test.
Okay. I just thought I would throw that out there. All right, anybody with any other questions before we get started? Nothing? Okay. Well, let's get started. All right, so we are in the PDF, we're on page 65, which is digital modes. Okay, so digital is just ones and zeros. Now, it can also be combinations of ones and zeros. So for instance, if it's 3 bits at a time, it can be 000, 001, 010, 011. There are 8 different possibilities. So if you take X bits at a time, you actually have 2 to the X different things you can code. So it's actually quite powerful. But essentially, digital is sending zeros or ones, and that's the only thing you send. So which of the following are digital communications modes? Packet radio, IEEE 802.11. That's a complicated way of saying Wi-Fi. And FT8 are all digital. What's included in a packet radio transmission? Okay, so a packet, if you include, let's say you write up a packet and send it to somebody, that's basically a bunch of information all wrapped up in an envelope, right? Or an email. Packet radio is basically that. What we send are data packets, which is essentially information wrapped up in an envelope. We have a header, we have framing, so we have the start and the end. We also have an address on it, just like an envelope. We also have a special thing in a packet called a checksum. So for instance, if I'm sending this message, hello, my name is Scott, that's 5 words, right? I could send a number, which is 5. Well, that would say, okay, if you got, hello, my name is Scott, that's 5 words. I told you that there are 5. So, okay, at least you know that you had the right number of words. If it didn't match, then you might have lost something. So that's called a check. For digital communications, it's called a checksum. We also send a header so we know where to address the information, and an automatic repeat request, which basically says, hey, you know, if I didn't get what you sent me, I know you sent me something, but there was definitely something wrong. I'm going to send a repeat request and say, please send it again. I didn't get it. So ARQ is, again, an automatic error correction method where the receiving station detects errors and says, I didn't get it, please send it again. So ARQ, automatic repeat request. APRS, okay, that's the automated packet reporting system. Now, I have a very quick example of APRS. My friend Rich last night sent up a balloon. And the balloon is solar powered. It has a little, it's actually a helium balloon with a solar powered transmitter on it. There's not enough sunlight to fire up the transmitter yet, but he sent it up from Eugene yesterday. And it, let's see, show lasts 12 hours. That's 24 hours. Okay. So this is using a website called aprs.fi. And it's based out of Finland. And essentially what we have is a track of all the information that has gone up into the world of packet, which is essentially digital communications, which then gets picked up and shared by different hams all over the place. And it basically is just ones and zeros. And so yesterday at about, what time did he put it up? 12:57, about 1 o'clock in the afternoon. He sent up a helium balloon with a transmitter on it, and exciting time. Hopefully when the sun really comes up, it'll start transmitting again, and we will see how far it moved in the middle of the night. And hopefully it didn't, you know, pop and crash to the ground. It's designed to operate at between 35 and 40,000 feet. So hopefully it didn't get sucked into an airplane engine and destroyed. So cross our fingers. As of last night, it was at 36,000 feet, and I believe still rising. No, it was floating around at about 36,000. So sometime this morning, we will see how far it's got. Let me pull that up and share it.
Are the senders of those responsible for picking them up when they fall, or did they just leave them as debris?
Well, usually they're not going to, if they do survive, I mean, the whole thing is only this big. It weighs 8 grams. So basically the equivalent of 8 paper clips. There's very little on it. It's a tiny little circuit board with a transmitter. And the wire that holds it to the balloon is the antenna. I suspect that if it's still in the sun, it would keep transmitting, but you'd need to be able to see it from the air. You'd need to be able to receive the signal from the air. So yes, we've talked about going out and getting them back, but the chance of actually doing so is quite small. But yes, it is something we've talked about. So there's the track that it took as of about 7 o'clock last night. And we don't really know where it went overnight. A lot of it depends on the winds at 36,000 feet. Okay, so that's APRS. It's a way of showing real-time tactical digital communications in conjunction with a map. So there you go. She puts it on a map. Information that can be transmitted by APRS. We have GPS position data. You can actually do text messages and weather data. So that particular balloon was saying, here's my altitude, here's the barometric pressure, and here's the temperature on board. Another digital mode is PSK31. That's phase shift keying. So if you remember, phase is, if you look at a sine wave, it's where it is in its cycle. So it's an instantaneous shift of the phase of the signal. There is a very slow mode that we use for keyboard to keyboard communications, like literally somebody typing and somebody else receiving it. It's called PSK31. It's 31 baud, and also that's about the bandwidth of the signal with 31 hertz. Very, 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 very narrow. Very efficient mode. Digital mobile radio. So we have a handheld radio. Now, this is an analog handheld radio. It uses analog audio. There's also something called digital mobile radio. Essentially, what DMR does is it takes your voice and converts it into ones and zeros, just like your cell phone does. And it splits one channel on VHF, like on your repeater, into two separate channels. And it splits them in time. So it says channel A, then channel B, then channel A, then channel B. Now channel A, now channel B. And your radio is synchronized with that. So you don't even know if you're on channel A that there's a channel B and vice versa. So it allows people to basically get twice as many signals onto a band. Wsjtx, that's it's also known as the FT8 protocol or JT65. There are several different ones. It's a very, very good protocol, digital protocol for weak signal work. So if you think of the weakest signals you can possibly think of, weak signal propagation, okay. Meteor scatter, by the time your signal hits a meteor trail, it's probably pretty weak. And Earth, Moon, Earth, by the time your signal travels 500,000 miles and bounces off the moon in the process, it's probably pretty weak. So those are perfect options for WSJTX. FT8 is a digital mode for low signal to noise operation. It's a very rudimentary communications method. Some people say that using it is sort of like watching paint dry, because you basically tell your computer, okay, make the contact with this person. It's not very interactive. However, for some people who don't really like interaction, or let's say you happen to be like, writing a proposal at the time for a grant or something, which I've done. And in the process of doing that, oh, look at that, I made a contact. So it's a way of just basically establishing contact between two stations and saying, okay, here I am. Okay, bye. So that's FT8. Mesh networking. A mesh network is a self-healing radio network that uses Wi-Fi equipment. And the benefit of this is that there's tons of Wi-Fi equipment out there. You basically take your Wi-Fi router and you reprogram it with a different firmware and make it so that it's, because we actually share a band with Wi-Fi. We're not allowed to talk to Wi-Fi, but we could easily modify the equipment so that it works on ham frequencies in ways that we can actually use. So essentially mesh networking is a self-healing digital network. So if you happen to lose a connection, it finds another way to get the information from one end to the other. And one of its best applications is in emergency communications. All right, so we're on page 68. We're on to station safety. Safety is really important. And this is the most important reason that we are in class is safety, how to not hurt yourself and not hurt anybody else. Electrical current flowing through the body. Basically, it can heat tissue. It can disrupt the electrical function of cells or cause involuntary muscle contractions. Anybody ever gotten a really good electric shock? It hurts. And my arm, when it happened, I was 10 years old, went from here to here, and I didn't even know how. I stuck my hand inside a vacuum tube receiver and got a 250 volt shock. Worst one I've ever gotten. Has anyone ever gotten a 480 volt shock?
I got a 277, which is half.
Well, no, 277 is single phase 480.
Right.
Yeah, that doesn't feel good, does it? Did it throw you across the room?
No, actually it hung on to me. It wouldn't let me go. I had to walk down the ladder to get off.
Geez. Okay. So it didn't require, and you're lucky it didn't require somebody else to yank you off. Wow. Yeah, I'm sorry that happened. That's not fun.
Does anybody else have 50,000 volts?
Yeah, actually that happens all the time.
Yep. And it hurts.
It does, it stings, but okay. So there's an important distinction here between voltage and current.
Yep, that's why I kind of brought it up.
Yes, that's an excellent point. Okay, so has anyone ever walked across the carpet and then zapped somebody on purpose? Just because it was fun? Okay, that's actually about 20,000 volts. But there's no current behind it. Basically, it's a high voltage, but very few electrons available to zap someone. Now, that's a very big difference because that's static electricity. There's very little current available behind it. However, if you happen to get a shock from 480 volts or 120 volts even, there's a lot of current available from that source. And current is what kills you. Electricity will stun you. Current kills you. So if there's enough voltage to get a current flowing, that's what will actually do you in. And that's why we do, that's why we have fuses. That's why we have ground fault breakers that trip at 10 milliamps, because that's not enough to kill you.
And that's part of the theory behind tasers as well.
Exactly. That's why tasers are what, 500,000 volts or something? Something ridiculous like that.
Yeah,
It's
right
enough
around
to
50.
it's enough to basically stun you, but not enough current to do any real damage.
Exactly.
Okay, in the United States, the black wire in a 3-wire cable is the hot wire. So there's hot, neutral, and ground. Hot is the black wire. Now, this kind of goes against what we think of when we think of 12 volts, where the red is the hot and the black is the common. In 120 volts, black is always the hot wire. So when you go to rewire the lighting in your house, remember the black wire is the one carrying the voltage. Okay, a good way to guard against electrical shock, use 3-wire cords and plugs. 3-wire means it has a ground. The ground is the green wire, very important. Connect all AC powered station equipment to a common safety ground. Again, that's the green wire. And install mechanical interlocks if you happen to use a high voltage circuit, like a transformer for a tube amplifier, which can run 3,000 volts AC. If you're going to do that, make sure you have an interlock switch so that when you open up the cover, it turns off the system, because otherwise you'll have 3,000 volts floating around inside. And when you stick your hand in, you might get a really, really big fatal shock. Purpose of a fuse is to remove power in case of an overload. The fuse, it should be installed with the hot conductor in a 120 volt circuit. And what color is the hot wire again? I think I heard someone say black. Black, okay. Why should you never replace a 5-amp fuse with a 20-amp fuse unless you really know what you're doing?
Overheat and pop.
Yep. You can overheat. You can allow too much current to flow. If you're running a space heater, you can set fire to the space heater instead of blowing a fuse. What hazard exists in a power supply after turning it off? You remember that we had those big capacitors that filter power? Well, those filter capacitors, if they're really big, can charge up a lot. And unless there's a resistor in parallel with the filter capacitor, or from the hot lead of the filter capacitor to ground, that charge will stay there, sometimes for a really long time. If you think of it like this, there's something called a TV. Anyone ever seen like an old school TV with a tube? Right? In order to make a TV work, you had to apply about 25,000 volts across it, because it's basically a big vacuum tube and it's full of vacuum. When you charge up a TV, it had about 25,000 volts on it. If you remove that vacuum tube that is the TV, it will still be charged up to 25,000 volts unless somebody has discharged it. So what people typically would do when they work on a TV is they would stick a screwdriver underneath the rubber boot on the TV, on the back end of the vacuum tube, and wait for the zap, which was it discharging the tube. Now, that's actually a form of static electricity, right? But it can do a lot of interesting things. So I once, when I was about 9 years old and was curious about things, I took a Well, actually, this is a perfect size. Everybody see this coffee cup? I had a capacitor this big that my dad brought home from work once. And it was a 5-volt capacitor, which was for a computer power supply. I hooked it up to a 9-volt battery and thought, oh, well, that's kind of boring. I took my voltmeter and measured it, and it was at 9 volts. I'm like, oh, okay, well, that's boring. Well, I guess I better discharge it. So it had these 2 big screw terminals in the top. I put 1 screwdriver here and 1 screwdriver here, and I went like this and crossed them together. And what do you think happened?
You
Anyone?
learned the hard way.
What did I learn?
There's still juice.
I learned about arc welding. That there was actually enough charge stored in that capacitor to melt chrome vanadium steel on 2 different screwdrivers. So there is enough stored in that to actually do some serious damage. But again, we can use that for good, you know, arc welding. I could, if I'd held them together, I would have ended up with 1 big screwdriver in the shape of an X. Which of the following is a safety hazard of a 12-volt battery? Short the terminals. If you do that, you can cause burns, fire, or an explosion. First of all, you get an enormous amount of current, which generates heat. A 12-volt storage battery is made of lead and sulfuric acid. If it gets overcharged or undercharged, or it discharges too fast, you get dissociation of the sulfuric acid, and you get hydrogen gas. Well, now you get a lot of heat and a spark and hydrogen gas, and then you get an explosion, and you get sulfuric acid flying everywhere. That happened to a friend of my parents once. Fortunately, he, as you should do, if you're doing something like that with a car battery, some people just put a rag on top of the battery to absorb the impact. He also, and I think this is a good idea, when he's making the connection, you turn your face away and wear safety goggles or both. Because if something goes wrong, you know, you get splashed with sulfuric acid, there's, you know, you don't really have a chance to get out of that. Typically, you don't have, you know, 50 gallons of water available to wash your face off. What hazard is caused by charging or discharging a battery too quickly? Overheating or outgassing. And again, that can happen with any battery. That can happen with a lithium-ion battery. That can happen with a sulfuric acid lead battery. It can happen with an alkaline battery. But typically, it's not as severe. The bigger the battery it is, the worse. And the fact that if it's got sulfuric acid, that can be a real problem because it generates hydrogen gas. Antenna and tower safety. Okay, this is your basic industrial safety standards. When putting up an antenna tower, look for and stay clear of any overhead electrical wires. You have to make sure that if anything falls, any part of an antenna or a ladder or anything falls, it's at least 10 feet from any energized power line. So that's the distance, 10 feet. You should never attach anything to a utility pole unless there's nothing on the pole at all, because those power lines up there that look really innocuous and really are quiet and don't do a whole lot of anything are actually probably carrying 12,000 volts. And besides the fact that if it's a commercial power line, you know, power pole, it's not yours. You shouldn't be up there. If you touch an antenna during transmission, you can get an RF burn, as I explained yesterday with my little handheld radio. When I was a kid, I also leaned forward, and we're going to get into RF burns and grounding and there's safety grounding versus RF grounding, and they're 2 different things, and it's due to the wavelengths that we're working at. I leaned forward on my grounded piece of equipment. It was connected to the safety ground in the wall. As I was transmitting, I leaned forward. I was using a microphone, and I got a big zap right on my lip. We'll explain that shortly. That's known as an RF burn. When climbing a tower, know what you're doing. You know, at least get a briefing on how to climb a tower. It's good if somebody teaches you. Use a tie off to the tower, and always use an approved climbing harness. That usually includes a shock cord, so that if you do fall, you don't just suddenly come to a stop. It actually reduces your speed. Because as they say, it's not the fall that kills you, it's how you land. Under what circumstances can you climb a tower by yourself? The answer is never. Always have somebody there, because if you have a heart attack or get stung by a bee, you are stuck up there. Under what let's see. Important safety rule when using a crank-up tower. A crank-up tower is designed to be cranked up to hold antennas higher up than they would normally be in the working on them position. And when you're doing that, it's important to never try to climb a tower that is extended unless it has safety locking devices put in installed. Because one of the worst things you can have happen is a tower falls over when you're on it. Another one is a tower suddenly retracts when you're at the top. So don't do that. A turnbuckle through tension guy lines. Okay, so if you think about a commercial radio tower or something, most of them are not freestanding. There's not enough strength and enough concrete in the ground to keep them standing by themselves. So from the very top, you'll usually have 3 wires that go from different points on the tower to the ground, far, far away from the base. It makes a nice little triangular pattern. So the next time you're out somewhere and you see a big tower, like a radio tower next to the side of the road, take a look and see if it's freestanding or guide. If it happens to be guide, each of those wires is handling a certain amount of tension. And they typically will have a turnbuckle that allows somebody to go whoop, 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 and tighten or loosen them. Now, what happens is in the wind, there's a lot of vibration, and those turnbuckles will tend to loosen up, which will reduce the tension on the tower. If that happens enough, guess what happens to the tower? You now have an imbalance and the tower falls over. So a safety wire through the turnbuckle is essentially something that keeps the turnbuckle from vibrating loose in the wind. Which of the following establishes grounding requirements for a tower? That would be local electrical codes. Wherever you live, there are local codes. There's also something called the NEC, which is a National Electrical Code, which describes how things should be grounded properly. Proper grounding method for a tower, it takes 8-foot ground rods. You actually have to pound the thing 8 feet into the ground. Some places this may be harder than others. You need to use one for each tower leg, and you need to bond them to the tower and to each other. When installing ground wires, you use short and direct wires. You avoid sharp bends, and you bond everything together with heavy wire or a conductive strap. And again, you can't use anything that has a sharp bend, because lightning doesn't like to go around bends. Lightning will go around curves. It'll follow in straight lines when it gets down to something. But if it has a sharp bend, it'll follow the path of least resistance. And very often, if you have a sharp bend, it will jump from the bend to something that you didn't want it to. And then your ground doesn't do a lot of good. Where should a lightning arrestor be installed in a coaxial feed line? And that's wherever the feed lines enter the building. There should be a grounded panel near the entrance to the building. Essentially, what that does is, here's a piece of coaxial cable, and it's something that's inserted into the cable. And here's the center conductor as it passes through, and the center conductor is actually connected to the ground. Huh? Why would you do that? Well, in here, there's a gas which has a very high breakdown voltage, like 10,000 volts, that normally there would never be enough voltage to break down and ionize the gas when you're operating. But if there's lightning that comes down through here, all of a sudden you have 10,000 volts, 20,000 volts, 50,000 volts, and it's actually enough to ionize the gas, and it forms a conductive path. So you can hopefully take your lightning strike and send it to ground before it gets into your house and destroys all your equipment. But what's the safest thing to do if you know there's a thunderstorm coming? What do you
Unplug
think?
everything.
Unplug everything. Yeah, disconnect all your antennas, disconnect the antennas, disconnect the power, just unplug everything. Okay, we're now into RF hazards and radiation exposure. Now, when we say radiation, we're not talking ionizing radiation. That's like X-rays and ultraviolet, which can cause, genetic damage. What we are talking about in this case is radiation, like radiation that can cause heating. That's typically the danger that we're looking at. Okay, so there's something that we have called an RF exposure calculator, which we'll get to in a second. Okay, so radio signals are non-ionizing radiation. How is that different from radioactivity? It doesn't have enough energy to cause chemical changes in cells and damage DNA. So it's not going to cause you to mutate, but as we know, if you throw a cup of water in a microwave operates at 2.4 gigahertz at about 1,000 watts, and it's certainly enough to heat up your water. Who is responsible for making sure that nobody's exposed to RF energy above the limits that the FCC sets? And that says the station licensee. Okay, so the question is, well, I'm decided to put up a ham station. How in the world am I going to make sure that nobody gets exposed to high energy? Well, there's a couple of things you can do. Number one, you can do computer modeling. You can use calibrated equipment and actually walk around your property and figure out what the power levels are like. The third one, though, is using this thing called FCC OET Bulletin 65. Right? Well, that's a lot of words. It's a lot of acronyms. And really what it means is that the FCC has come up with these standards, and they have a calculation method for doing this. Well, because hams are good at doing things, we like technology. Somebody decided, it would be a good idea to computerize this and come up with an exposure calculator. So let's say we're running 25 watts and our antenna is a dipole. Notice that we have dBi. Well, remember yesterday we were talking about dBd. That's dB with respect to a dipole. An isotropic, or I, is a special antenna that doesn't exist in nature. It can't exist. It's an antenna that has the same radiation pattern, the same amount of strength in all directions. A dipole is going to have 2.2 decibels of gain compared to that. So we start with dBi. So let's say we have a dipole. We have a dipole that says use 2.2. Okay, let's say we're 3 meters from the antenna. So we're only 10 feet from it at 144 megahertz, and go. Okay, so the legal limit is in a controlled environment, which means that everybody who's in that area, you have fences up and things like that, 1 milliwatt per square centimeter, we're at 0.094. Okay, if it's an uncontrolled environment, that means you put it on the roof of your car and anybody can walk by. Well, when you're transmitting, it's about 1/5 of that limit, and it's still safe. Okay, but now what we're going to do is we're going to take this antenna and we're going to replace this antenna with a high gain antenna. Let's say we have 14 decibels of gain. And all of a sudden, guess what? Not safe. So if it's not safe, how do we prevent people from getting hurt? Well, you can reduce your power. Let's go down to 5 watts. And at least for some of the time, it's okay. Or let's go back to 25 watts. You can put up a fence and make sure that people don't get to within 30 feet of it. And now it's safe again. So this is a really useful tool to have. And in fact, every ham is required to do this on their equipment, no matter how much power they're running. Okay, the definition of duty cycle for averaging time. Basically, the duty cycle is the percentage of time that a transmitter is transmitting. And what's nice about that is, let's say you have a system where that your maximum duty cycle is 50%, half the time transmitting, half the time receiving. So if you have an average power of 10 watts, that means you can do 20 watts transmitting and 0 watts when you're listening for half the time. So if you change the duty cycle from 100% to 50%, you can actually double your transmitting power by 2 to get the same average as running 100%. Why do exposure limits vary with frequency? People are resonant at certain frequencies, believe it or not. We have a typical size, and that makes our bodies resonant at certain frequencies, which means we absorb more energy at certain frequencies than others. That is taken into account when you start doing your RF exposure limits. And it turns out that we have our lowest value of permissible limit at 50 megahertz, which if we look at the chart, we will see that that is the 6 meter band. So we have the lowest permissible exposure limit on the 6 meter band because we're about a quarter wave long. What factors affect the RF exposure of people near an amateur station antenna? Well, you got frequency and power level, distance to the person, and radiation pattern, which we just showed. And what's nice about that calculator is that it's really easy to just change those values and see how everything changes. If your RF exposure evaluation shows that people are being exposed to excessive RF, okay, so let's say that you have a house where, let's say you live in a townhouse and you put up an antenna in your attic. Okay, so I used to live in a townhouse. What about the people next door? Can you control when they go into that area of the house that's under that's getting a lot of exposure? And the answer is no. If you live in a single family house and you put an antenna in the attic, you know that people are not going to be exposed because nobody's going to get that close. If you have a backyard that's on common property, for instance, you put up an antenna, anybody could walk by. That means that people can get exposed, and they don't know that they're getting exposed because they don't really know if you're transmitting. And for the most part, you can't feel RF energy unless you touch the actual, touch the antenna. The other thing is, though, if you have a backyard where you have a fence and you say, caution, live antenna, that's basically saying, okay, I've established this area as a do not enter area. That is now something else. You've basically said that anyone who comes in this area should know that, right? Okay, so you can relocate antennas. If you relocate your antennas, that means that people can't reach the antennas that would normally be able to. How can you make sure your station stays in compliance? Every time you change a piece of equipment. And that doesn't mean, okay, I replaced a 100-watt transmitter with another 100-watt transmitter. It means if I replaced an antenna that had 3 dB of gain with one that has 10 dB of gain, that's a significant change. If I put in an amplifier and I went from 50 watts max to 1,000 watts max, that's a big deal. So you would need to go through and redo it. And hopefully you would do that before you actually spent the money to do it, to figure out if it's something that you really should do. Okay, the next one, station setup and operating controls. So we're on page 77. Okay, so we're going to talk about wiring and why you do certain things. So let's say you have a power supply right here. And what's the typical voltage of a power supply for mobile equipment? How many volts?
50?
12 volts DC. Okay, so we have a plus and we have a minus. And this goes to our equipment right here. So here's our transceiver. XCVR is a transceiver. Okay, so let's say we're going to do Ohm's law again. Let's say that our transceiver has a current draw of 10 amps. Okay, and it nominally requires 12 volts at 10 amps. Okay, so what we're going to do is do our Ohm's law thing, and we're going to assign a resistance here. Now, because a wire is not a perfect thing, it has resistance. It's not zero resistance. An ideal wire has zero resistance, but this is not ideal. What we're going to end up with is a voltage drop that is caused by that resistance. And what is that voltage drop? E is equal to I times R. We always go back to Ohm's law. This is how, again, 90% of problems are applications of Ohm's law. Okay, so how much current are we going to be drawing from that transceiver? We're going to be using 10 amps, right? Okay, so we're going to figure out what VR is, the voltage in the resistor, across the resistor. And we're going to take a voltmeter and go like this. And we're going to measure our plus and our minus, and we're going to have VR. If there's no current flow, we're not going to have any voltage drop at all. But now we have current flowing. We're going to say that it's 10 amps, and we're going to say that this is a 1 ohm resistance. Okay, what's 10 times 1, everybody? I hope it's 10 volts. All right, now what we're going to do is we're going to draw our circuit. Here's our power supply. Here's 12 volts. And here's our resistor. And we know that we saw 10 volts dropping across of that. And here's our load, our transceiver. And then this is connected back. Okay, if we lost 10 volts in our resistor, how much voltage is left for the radio?
2.
We have 2 volts left. Will the radio work? Definitely not. So what does that mean? Well, I mean, as far as we know, we designed everything right. Where's the problem? Is it in the radio? No. Is it in the power supply? No. Where's the problem?
It's in the cabling.
It's in the cabling. Yeah. So, okay. Now, if you start looking at wire basically looks like this. All right, wire has a cross-sectional area and it has a length. Resistance is affected by area and it's affected by the length. Because DC in particular uses the entire area of the wire. So if you increase the area, the resistance goes down. If you increase the length, what happens? The resistance goes up. So how do you keep your resistance as low as possible? You want cable that's really, really fat and really, really short. So we make our connections short and we use the fattest wire we can. And that minimizes the voltage drop. So if we do a good job here and we take this resistor and instead of being 1 ohm, we replace that cable so that it's 0.1 ohms. We are down now to 1 volt of drop, which means we have 11 volts left for the radio. Well, that's better. Let's even use better cable, 0.01 ohms. Now we have a voltage drop of 0.1 volts, which means we have 11.9 volts left for the radio and everything's fine. Now, the other thing we could do if we really wanted to is we could take this power supply and adjust the voltage up slightly to account for the voltage drop in the cable. And in fact, we sometimes do that. The other thing when we're talking about power is, let's say that we now have this cable and everything is good. And we have cable that can handle a 10 amp draw, which is what this radio is handling. And that's what the radio is using. Okay. Now we're going to take this radio and we're going to say, how much power do we get out of this radio? How much power is it using? P equals I times E. It's 10 times 12 is how many watts? 120 watts. Okay, so what if I were to tell you that this is actually a 50-watt radio? What would that mean? Where's the other 70 watts going?
Heat.
Heat. So your radio, when you're transmitting at full power, is getting pretty warm. If you look at a mobile radio, it typically will have a really big heat sink on the back because You don't have 100% efficiency in the transmitter amplifier. And you're also turning the lights on. There's a microprocessor in there. You have a microphone that maybe has some lights on it. So essentially what you've got is you've got less than 100% efficiency. So when you're going to pick a power supply, even though, okay, let's do this. I have a 50-watt transmitter. If that was 100% efficient, this would be about 4 amps. Well, clearly that is different from 10 amps. So I would be very comfortable using a 10 amp power supply here. But what if instead I decided I was going to use a 4 amp power supply? What would happen? What would happen if I tried to transmit with it? Come on, somebody guess.
Well, it wouldn't be enough. Is that right?
That's right. That's right. The power supply would basically say, I can't deliver enough, and it would shut off. You're trying to pull too much current, and it would just turn off. It would protect itself. So you're drawing too much current. I'm done. So that is why it's important when you're picking equipment, when you're picking power supplies, to make sure that everything is sized properly, and it's usually sized bigger than you think it needs to be. So next question, which of the following is an appropriate power supply rating for a typical 50-watt transceiver? Well, it's going to be 12 amps. We know, or sorry, it's going to be 13.8 volts, which is a car battery. And there's the question. Is it 4 amps or is it 12 amps? What do you think? Which one?
12.
It's 12 amps, right? Because you account for inefficiency, you account for all the other loads that the radio has built into it. Okay, like I said, Ohm's law solves 90% of problems. What signals are used in a computer radio interface for digital mode? You have receive audio, transmit audio, and transmitter keying. Okay, for those of you who are going to be interested in doing digital stuff, interfacing a computer to a radio. You have really only 3 wires that are necessary. 1, 2, 3. Number 1, you have to get the audio out of the computer into the radio. So that's your speaker output of the audio, output from the computer and into the microphone input of the transceiver. You also have the radio sending audio out through its speaker into the microphone input of the computer. And then you also have this one in the center, which is push to talk, which is essentially somebody hitting the radio's push to talk button and keying the radio. So that comes from the computer and turns the transmitter on. That's the push to talk function. So how are the transceiver audio input and output connected in a station to operate using FT8? And you use the audio input and output of a computer running Wsjtx software. So that's exactly what you would think it would be. Basically, the computer's running the software, and the computer uses the sound card built into the computer to send audio to and from the radio. Which of the following connections is made between a computer and a transceiver to use computer software when operating digital modes? Okay, well, again, there are multiple choices. Line in is basically the microphone. You connect that to the speaker of the radio. And the out goes to the microphone. So there are really 3 different ways of asking the exact same question. So somebody saw fit when they were writing this question pool to say, okay, this is really important. We need to be able to phrase this in multiple different ways. If you understand that the computer has to be able to talk to the radio and vice versa, you'll be fine. Which of the following could you use to cure distorted audio caused by RF current on the shield of a microphone cable? Okay, so now what we're going to talk about is that same thing that we used inside a transformer, except this is a little bit different. We're going to make a donut. And this donut is a mixture of iron and nickel powder with glue. So why would we do this? What do you know about iron and nickel and things like that? They have a name.
They conduct electricity?
They don't really conduct electricity that well. They are ferromagnetic materials, which means that they are really good at handling magnetic fields. Okay, so let's say that you have a donut that's made of powdered nickel and iron that's then baked with glue into the shape of a donut. And you can take a wire and do this with it. If you have energy on the wire in the form of current, what will that make? What does a current flowing through a wire create?
Electromagnet.
In particular, it'll make a magnetic field, right? Now, if this particular material that you use has a susceptibility to magnetic fields at a particular frequency, it will tend to constrain the magnetic field inside here. Well, if it goes around and around and around enough times, what ends up happening is that it starts to get warm. Well, if it starts to get warm, what is your energy obviously turning into?
Heat.
It's turning into heat. Okay, so this is actually a good thing because sometimes on your cables, you have audio plus RF energy floating around on it. Well, if it happens to have RF energy, the audio is a low frequency. The audio passes in one side and out the other. And what happens to the RF energy? The RF energy turns into a magnetic fields too, but this material is really good at basically crunching all that RF energy and turning it into heat. So what you end up with is a filter. This is known as a ferrite choke. Anybody know where you have one of these? If you're using a computer, there's probably one really nearby. Anyone have one that they can show me? If you're using a computer, there's probably one really nearby. Do we have any? All right, that means I'll go grab mine. Here we go. Everybody see this? That little donut there? That is on my power cord on my computer. And what is that for? That basically takes anything that isn't DC and runs it through that donut, turns it into a magnetic field and keeps it from getting into my computer. And that's an RF choke. Okay.
So does that just keep the energy in there, or what happens to it once it's in the...
turns into heat.
Okay.
Once it becomes heat, it can't hurt me anymore. So, and that's known as a ferrite choke. So a ferrite choke is really good. And actually on my computer out at my station, I have a cable on which I have 5 ferrite chokes. Now, why do I have 5 ferrite chokes? Anybody?
More is always better.
Yeah, and 4 was not enough. When I had 1, 2, 3, or 4, and I keyed up my radio, what ended up happening was I locked up my computer. When I put the 5th one on, it didn't happen anymore. So I have 5. A lot of experimentation. Which of the following is preferred for bonding at RF? Okay, that is a flat copper strap. Now, there's no real explanation as to why. Okay, so what we're going to do is take a little moment here to draw a round cable. Okay, now if I am using DC, my DC current flows uniformly throughout the cross section of the cable. Right, I get to use the entire area of the cable. However, if I am using AC, and remember, radio is AC, and our wall current is AC too. The higher the frequency I use, the more the current, believe it or not, likes to flow as close to the outside of the conductor as possible. In other words, you get no current on the inside, and you have a little bit as you get no current at the center, and it gets a little bit stronger. And when you get to the outside, all of your current, virtually all of your current is flowing on the outside, not on the inside. This is known as the skin effect, and it is an AC thing. It's only for AC. What that actually means, though, if you think about it, is if I have a conductor, if I really wanted to, couldn't I basically just make it like that with a hollow center if I was doing it for radio frequencies? What do you think?
I would think that would vary a little bit, so you need the extra space.
Yeah, actually, and in fact, you can do this. You can actually have RF energy on a conductor that's hollow. And in fact, in order to save costs and save weight, this is actually done on bigger cables because there's nothing that would flow in the center anyway, which is actually kind of cool. It's taking advantage of this thing called the skin effect. But now, let's say you have a certain amount of copper and you want the lowest resistance possible, and you're using AC. Would you take that and make it in the shape of that, or would you make it in the shape of a flat piece? Where do you get the most surface area?
The flat.
Yep. So this is actually a flat strap or a conductive strap. And when we're talking about RF grounding and bonding, we typically want to use a flat strap because that allows the greatest amount of RF current to flow with the least resistance. But this is actually a very important distinction with the skin effect, because like if I were to draw this cable, ready? Here we're going to draw a coaxial cable. Okay, so we're looking at a coaxial cable end on. How many surfaces are there that can carry distinct signals? What do you think, everybody?
2.
Nope. 1, 2, 3. The inside and outside of a cable can actually carry different signals because it flows on the outside. So this and this, signals 1 and 2 are equal to each other. Signal 3 is something that can be picked up from outside and carried down. And so with coaxial cable, typically what we do in order to make sure that that doesn't get carried into our station is here's our cable. We would actually run this like this. We would take our cable and go like this. We'd wrap it around a toroidal core, and that wouldn't do anything to the signal that's on the inside. But what it would do is if there's any signal that managed to get trapped on the outside, that would get killed because we didn't want it anyway. It wasn't supposed to be there. Yes, fun with RF. Okay, where should the negative power return of a mobile transceiver be connected in a car? And you want to go to the 12-volt battery chassis ground. You don't want to go to any random place on the frame. And why not?
So I think you don't know what else was connected to it.
Yeah, and you don't know how good of a job somebody did when they're building the car. You don't know how good those welds really are. So you don't want the car body to be required to be the return path for your 20 amps. 20 amps goes in, 20 amps has to go back. So you want to go back to the nearest place to the battery that you can. Typically, there are two good spots. There's the negative terminal of the battery and there's the engine block itself. Those are pretty reliable. How can you determine the length of time that equipment can be powered from a battery? Okay, this is really, really helpful. Okay. Batteries are measured in ampere hours. Sometimes they're measured in watt hours. All right. So what is the difference between a watt and an amp? A watt is power and an amp is what? Current. Okay. So P is equal to I times E. So the only difference there is the voltage. So let's say that we have a battery that is rated at 75 amp hours. Well, that has a couple of different meanings. Number one, it means you could, in theory, draw 1 amp for 75 hours or 75 amps for 1 hour. And in fact, it doesn't quite work that well, but essentially it's very close to that. Now, I would never really want to pull that much current out of a battery that fast for that short of a time. So if I were to do that, I would go with a bigger battery. But typically I could pull, let's say 5 amps for 15 hours. So that's a good way of figuring out how long a battery is going to last. Now, if let's say that the battery was rated at 12 volts, a 75 amp hour battery would be also 75 times 12 is a 900 watt hour battery. That's another way of describing the exact same thing. Except for the fact that if it was something other than 12 volts, that rating would change.
I got a quick question. How do you find what particular things draw?
Well, some of it's experimental, and a lot of times it's actually the rating on the equipment itself.
Okay.
Well, and let's say that you have a 50 amp hour, let's say you have a 50 watt transmitter. You can basically assume 10 to 12 amps. You just say, okay, well, here's my general rule of thumb. 50 watts at 12 volts, P equals I times E. So I is equal to, that would be 50 divided by 12, which is about 4.3 amps or so. 4.2. Okay, so now we have to look at efficiency. Assume that we're about 50% efficient. And that's power out divided by power in. So or we can say, in this case, it's current out versus current in. And that's 4.3 divided by something. So that's 8.6 amps. And then you just basically say, okay, well, it's got to be a little more than that. We could probably get away with a 10 amp power supply. It's all, the other way to do it, of course, is to hook it up to a really big power supply and then transmit and measure it. The way you do that is here's your power supply. Let's say this is a 50 amp power supply. So it has plenty of oomph behind it. And here's your load. Get rid of that. And we break the circuit right here and we put in an ammeter in series, plus and minus, and we measure this at 9.6 amps when we're transmitting full power. Okay, there we go. Now we know what it is. But more often than not, a manufacturer is going to have a specification for it. Okay, operating controls. All right, any more questions on batteries before we move to operating? Okay. What's the effect of excessive microphone gain? That's basically doing this. Do I sound distorted to anyone if I do that? If you have too much microphone gain, you're basically getting to the point where the amplifier can't reliably amplify it anymore. You're exceeding the ability of the amplifier to do its job, and you're all distorted. The results of tuning an FM receiver above or below a signal's frequency, it'll be distorted. Basically, FM likes to be tuned properly. And just in case anyone's curious, we're on page 80 right now. What can be entered on how do you enter a transceiver's operating frequency? Well, there's two ways to do it. So I'm going to hold this up here. I can turn the knob, make sure this is unlocked. I can turn the knob. Everyone see the frequency changing? Or I can use this keypad and directly punch something in. So keypad, this is actually called a VFO knob, or variable frequency oscillator. This goes back to the days when we were actually making our own frequency internally, and we'd actually make a big adjustment. I can show you something that looks like that by showing you this right here. There we go. Anybody recognize a radio that looks like that?
Yep.
Okay, well, that's a Collins S line from about 1962. That radio has some big knobs right in the middle of each one. Those are VFO knobs, or variable frequency oscillator. And they would actually control a variable capacitor and rotate it back and forth and change the capacitance of a circuit, which would then be connected to an inductor, and which would generate a frequency that you would then change, which would change the frequency of the radio. These are collector's items, by the way. Okay. An easy way to enable quick access to a favorite frequency, store it in a memory channel. This particular radio, which is commonplace these days, this has 200 memory channels, maybe more. This one has 1,000 memory channels. So you'll never run out of places to store memories, to store frequencies. The scanning function of a transceiver tunes through a range of frequencies to check for activity. Okay, the purpose of Squelch. All right, so I'm going to try to turn on my original audio. And here we go. Okay, can everybody hear this? You hear static? All right, this is Squelch. Does everybody like that? That's Squelch. Squelch off, Squelch on. Squelch allows you to mute a receiver's output when there's no signal of interest to be heard. That is the meaning of Squelch. Okay, how is Squelch adjusted so that a weak signal can be heard? Well, okay, let's say that I want to hear something that I know is going to be weak. I would actually intentionally turn it off so that I could always hear it, because the signal itself might not be loud enough to break the squelch, as it's called. What is meant by repeater offset? Okay, so now we're going to talk about repeaters a little bit and how they work. Okay, so we're going to pick a frequency that is published. We're going to go to a website. Well, we're going to take information from a website called Repeater Book, and we're going to pick this repeater, 146.72. with a negative 600 offset and 100.0 hertz tone. Okay, so these are typical things that you're going to see published in something called a repeater book or a repeater guide, or anybody that owns a repeater or uses a repeater will see these. This is the center, this is the frequency of the repeater, this is the offset, and this is the Ctcss. This is the offset, and this is the frequency. Okay, so the way that a repeater works is that you have, let's say, a mountaintop. And on this mountaintop, you have a little house. The house has a transceiver in it, and you have an antenna up on top of a tower. So you are down here on the ground with a handheld radio. This repeater says, and it's published, 146.72 megahertz. That is a 2-meter band repeater. And it says that it has an offset of negative 600 with a 100.0 tone. Those are the things that you will see. What that means is that the repeater is listening on 146.12 megahertz. It is transmitting signals on 146.72. So if you want to hear it, you will tune your radio to 146.72. So I will tune my radio to 146.72, and I will be able to hear what the repeater is saying. If I want what I am saying to be heard, I will use a negative offset and go negative 600 kilohertz or negative 0.6 megahertz. That's why it's important to be able to convert units. And I will transmit my signal. Well, we know that 146.72 minus 0.6 is 146.12. Well, that happens to be exactly where the repeater is listening. It's listening on a different frequency than you are. You are listening for the repeater's published frequency, and it is listening for your input. 600 kilohertz lower than its transmitted frequency. It's also listening for this 100.0. This is known again as a Ctcss, which is a continuous tone carrier squelch system. Basically, this is a very low tone. It's 100 hertz, so it's like a rumble. But there are 38 different tones that it could be. And if you are not transmitting with the proper one, the receiver will say, I'm not getting the right tone. That's not a real signal. So if you set up your radio so that it's transmitting with 100.0 hertz subtone, as it's called, and the receiver listens to the audio up here at 100.0 hertz, and it says, oh, yeah, it's there. What it's going to do is take your signal, run it through a controller, and then send it out on the other frequency simultaneously. Which means basically that to anybody else, let's say that a friend all the way over here on the other side of the mountain with a radio, it sounds as though your voice is being transmitted on 146.72 megahertz. And it sounds as though you are standing up on top of this repeater tower. Which, if that repeater is 3,500 feet up, that's a really good thing. Because then anybody who's in range of that mountaintop can basically act as though and sound as though they're on top of it. So that is why when we talk about repeater offset, it's very important to understand how that offset gets set in your radio and what your tone has to be. Now there's another one called DCS, which is digital carrier squelch. And this is another, except it's digital. It basically follows your radio follows a sequence of tones or sequence of frequency shifts. And this will be something like D023, which is a planned sequence of frequency shifting. And if your radio isn't doing that, the repeater will say that's not real. If your radio is doing that, it'll say, yep, it's programmed right. Your signal is legit. And that's why it's very important to understand how to set up your radio. So repeater offset, very simply, is the difference between a repeater's transmit and receive frequencies. Function performed with a transceiver and a digital mode hotspot. You can actually have a digital mode hotspot, something like a zum spot, where you basically have a hybrid radio/internet access point, and that allows you to communicate to the hotspot using your radio, and then it gets transferred over VoIP to the internet, and then it can be transferred to another repeater anywhere on the internet, literally anywhere. It could be in another country. It could be, 5 miles away. There's a lot of hybridization right now between radio and the internet because we have this thing available, and there are a lot of people who have their ham licenses who are very, very tech savvy when it comes to, internet protocol. So if that protocol exists, if the internet is working, you might as well figure out a way to use it to extend your range. A talk group on a digital repeater. Okay, notice there, again, there's digital and analog. A digital repeater is for digital voice. So again, your voice got transferred into a digital format and then is either group A or group B. A talk group on a digital repeater is a way for users to share a channel at different times without hearing the others. So you can have group 1 and group 2, or group A and group B. And you set your radio up so that it is operating on either group 1 or group 2. Now, you can also have a digital repeater with a gateway, if you want, where the gateway connects the repeater to the internet, and in addition to other stations locally being able to hear you, there could be other people on other repeaters who are in the same talk group who can actually communicate on that repeater with you. So you could be 3,000 miles apart using a handheld radio, and if you're on the same talk group, if the internet is up, it connects them seamlessly. A DMR code plug. DMR is digital mobile radio. A code plug is basically a program for something like this radio for how to communicate with different talk groups all over the place. This particular radio stores 120,000 different locations. That it has memory for basically talking to 120,000 different stations. Believe it or not, this isn't big enough anymore. The newer radios are closer to 500,000. So it'll store 500,000 different locations, people you can talk to using your digital radios. That's known as a code plug. How is a specific group of stations selected on a digital voice transceiver like this? By entering the group's identification code. If you are taking a test today, you may notice that some of the guys who are giving the exams have a handheld radio and are able to talk to each other even though they're in different cities. And that's because they're using digital radios and are able to connect through the internet with those radios. Okay, so if you enter the group ID, you can connect to that group. What is the purpose of color code used on DMR systems? Color code establishes groups of users. Which of the following must be programmed into a D-star digital transceiver before transmitting? You have to, anytime you're transmitting digitally, D-star is another form of digital communications for voice. You just have to put in your call sign. Okay, so now we're talking about HF transceivers. And for that, I'm going to pull up our handy dandy right there. Here we go. Can everybody see that okay?
Yes.
Okay, here we go. I'm going to turn the audio back on. Can everyone hear it? Nope. That's right. When I share it every day, I have to reestablish that. There we go. Now you should be able to hear it. Okay. So what we're going to do is we have multiple bandwidth choices. I can show you this by doing this. Okay, so if there are a lot of signals, say, notice you can hear multiple different things at the same time. If we're listening for one thing, how many things do we want to hear at once? Ideally, just one. We have multiple different bandwidth choices. And we can filter by changing our filter bandwidth so that we're only hearing the thing that we want. Now, let's say that we went over to a voice band and tried doing that same thing. Here we go. Can anybody understand that?
Not very well.
Exactly. Let's go to another one. Anyone? I know I can't. So, but let's do this.
In my smartphone. Hi, good evening, all the best.
Okay, so it's important to be able to set. It's important to be able to set the bandwidth of your filter. What we have here, right there, is a filter bandwidth. See the yellow bar? So we have our low cut point, and this is our high cut. So this is actually a band pass filter. I can take this filter and I can move the pass band up in frequency. I can move it way up in frequency to the point where you can't even hear anything. I can also move it way down in frequency. And this would be called a low pass filter. This is essentially becomes a high pass filter. And if it's only allowing a certain band of frequencies, that would be known as a band pass filter. So this is all being done digitally, which is nice, because it used to be that when you bought a radio, you got like 1 or 2 filters, and anything else, they were actually mechanical filters made of crystal, like quartz crystal, and you had to buy another one to replace it. And for a $500 radio, that filter could end up costing you another $200. So it was kind of a big deal. So the fact that these things are available now and they can do it digitally is a wonderful improvement. For Morse code, you would typically look for about a 500 hertz bandwidth. For single sideband, you're typically looking for about 2400 hertz. 2400 hertz is perfectly adequate to listen to what you want to listen to, if it's voice. So an example of an RIT or clarifier, this is when we would use something called a clarifier. Okay. So let's say that we tuned this guy in, and we went to upper sideband. But it sounded like this. Does that sound right? Okay, and it's not right. Now, let's say that the other station was hearing your signal just fine, but he sounded like that. So you change your main tuning. That makes the other station sound right, but now you sound wrong. So that other person says, oh, that's messed up, and changes their frequency. And the next time you hear it, they sound wrong to you. So essentially, you basically go like this, and you keep moving up or down the band, chasing each other. Receiver incremental tuning, or this thing called a clarifier, allows you to adjust the receiver frequency without adjusting the transmit frequency. So that's receiver incremental tuning. So if the voice pitch sounds wrong, you can use the RIT to make a minor adjustment without changing your transmit frequency. The term clarifier is specifically a Yaesu term. Yaesu is one of the manufacturers of a lot of equipment. It's basically an RIT, or receiver incremental tuning. The function of a transceiver's PTT input. PTT means push to talk. And when you ground that signal, it switches from receive to transmit. Now, this is actually really important. Most transceivers, if we take that word transceiver, that is a transmitter and receiver. Now, if you look back at this picture, what you'll notice is that there are 2 boxes on the desk, right? There's actually 3, but there's 2 of them that look about the same size. There's a receiver and a transmitter, and the thing in the middle is a transmit-receive switch. So when you wanted to convert from transmitting to receiving, you would actually have to reach across and grab a switch and throw the switch to bring on the other piece of equipment and turn off the first one. And that's known as a TR switch. When we have this thing called a push-to-talk button, the push-to-talk button automates that process because everything is in one piece of equipment now. Okay, station equipment, page 84. What is a transceiver? We just did that. A transceiver is a portmanteau of the words transmitter and receiver, mashing them together into one new word called a transceiver. The device that converts RF input and output of a transceiver to another band is called a transverter. A transverter is a portmanteau of transmitter converter. So this is a transverter. where you have, let's say, one frequency, we'll call it 28 megahertz, and you mix this with another frequency, let's say 194 megahertz, and what comes out is the sum and the difference and multiples and lots of other things. So what comes out of this is 222 megahertz, and you also have 166, and you have 194 and 28 and a whole bunch of other things. So what we're going to do is look at our frequency chart, and hope I can find it. I know I opened this band plan, and I'm going to stop sharing this and open this. And what we're going to notice is, does everybody see that there's this, on the band plan, there's this thing called the 1.25 meter band? Everybody see that? Right? As a technician, you have access to the 1.25 meter band. And notice it's at 222 megahertz. However, this is not a ham band in Japan. And because a lot of equipment comes from Japan, that means that they don't really focus on this band very much when making equipment. So there's very little equipment available for it. So in order to use this band, either you pay through the nose for a piece of equipment, or you can generate these frequencies yourself. To generate these frequencies yourself, you use something called a transverter. And again, you'd put in 28, and you'd have a 194 megahertz oscillator. And one of the things that comes out is 194 and 28 and 166 and 222. And then there's some other stuff as well. The one that we care about is this 222. The core of a transverter is something called a mixer, which is a nonlinear device that multiplies and adds multiples of frequencies and subtracts them from each other. And essentially what you get is a mess of frequencies coming out that looks kind of like this on the frequency graph. Okay, now let's say that this one is 222. What would I do to make sure that I didn't get the other ones and I did get the one that I wanted? I would have to build something. What would that be? It has a name. Starts with the letter F.
Filter?
A filter. And I would actually specifically build a bandpass filter that looked like this, that allowed the 222 megahertz band to come through and not the others. And what is at the core of my filters? Two different devices that are frequency dependent. What are those again?
Capacitor and inductor.
Yep. Those two devices are at the core of every tuned circuit, unless it's done digitally. Those are at the core of every physical tuned circuit. There are capacitors and inductors in literally every mechanical tuned circuit that you will ever find. Because if you do that, and you pick your capacitor and your inductor, and maybe you add another capacitor here and another inductor here, or depending on how you want to do it, essentially what you end up with is a peak frequency and then rejecting frequencies. In which case you basically have a filter that looks like this in series with a filter that looks like this. And if you do that, you basically get the intersection of the two, and you build a bandpass filter. Every radio has a bandpass filter in it, and that is to make sure that other frequencies don't interfere. It's one of the things that's at the core of every piece of radio equipment. Okay, so that's called a mixer. A mixer is at the heart of a transverter. The device that increases the power output from a transceiver. How do you make a bigger copy of something? What do we call it?
An amplifier?
An amplifier. And since we're dealing with RF, we use an RF power amplifier. Okay, so most of them are made of transistors these days. They don't have to be, but most of them are. You'll remember that it follows a curve that looks like this. Here's your in and here's your out. We have this range called the linear range. And again, we have cutoff and saturation. This is the interesting range where everything is almost flat. Again, known as the linear range. Now, what you'll find is that if you buy a power amplifier, like an external power amplifier designed to hook up to a handheld radio that might take 2 watts input and put out 50 watts output, it'll have a switch on it that says CW, SSB, or FM. Well, the reason that is because if we're using, let's say, voice, we want an adequate and good representation of what we're actually saying. If we operate outside of that linear range, we get distortion. We don't want distortion typically. If we have single sideband, it's an amplitude modulated signal. We want it to be clean. So single sideband will use this linear range. However, if we're using FM, the way that FM works is that we're only interested in the frequency of the particular signal. When it gets to the receiver, it gets trimmed amplitude-wise so that it's always the same, which basically means that anything that's higher or lower in amplitude gets cut off. So it really doesn't matter. All that really matters is what the frequency is at any given time. So an FM amplifier can operate way up here in the saturation range or use the entire range. And what that means is the FM amplification can actually be more efficient. We don't have to bias our amplifier quite as carefully. So that's why there's a switch on it. So it has to be set to the proper operating mode. Okay, now here's something, and we're going to take a break in just a couple minutes. What describes the ability of a receiver to detect the presence of a signal? Okay, ready? I want everybody to unmute themselves who feels like doing so. Okay? Okay, and I'm going to pick on Victoria because you're all the way up at my upper left corner. I want you to whisper something really quietly.
Oh, how are you? I'm doing well. What's going on?
Okay,
is it going?
Good. Okay, was anybody able to hear that?
Yes.
Okay, now if she got even quieter, some people would probably not be able to hear it. That is the sensitivity of your ears. That's a receiver's sensitivity. Sensitivity is the ability to hear things that are quiet. Okay, now ready? On the count of 3, everybody say your name. Ready? 1, 2, 3. Okay, how were you at picking out everyone's name? Okay, but maybe you could hear one, right? Now, if we could make our receiver so that we could actually filter it so that we could actually hear individual names separately, that would be known as selectivity. We could selectively listen, and I've been, as have most people here, been accused of having selective hearing sometimes. That's exactly what we're talking about. The ability to hear just one thing in a crowd of other things. That is a receiver's selectivity. Okay? So, to improve the sensitivity of a receiver, you can use an RF preamplifier. All right, so now we're getting into system design a little bit. And so we're going to put an antenna up on a tower, and we're going to have a cable coming down from the antenna into a transceiver, an XCVR. Okay, so we have a signal coming in that by the time it gets there is minus 124 dBm. Now that M, remember we've used D and I, now we're using M. That is with respect to a milliwatt. So that signal is actually, if we start looking at how many times different it is, remember if we go negative 10 dB, that is 1/10. Does everybody agree with that? Okay, so if we have negative 124, that is negative 10 and have 12 of them, and a minus 2 and a minus 2. Or let's go approximately equal to a minus 3. We'll have a little bit thrown in there. So this is 1/10 times 1/10 times 1/10 times 1/2. Or roughly 0.0000000000005 watts. Now, does everybody see? Oh, I'm sorry, milliwatts. So let's get rid of that and put another 3 zeros there. 0.0005 watts. Now, does everybody see why we use decibels here? To say that it's minus 124 dBm is the same thing as saying it's that many watts. Would anybody prefer to use all those zeros? I don't think so. Okay, so we describe it using decibels compared to a milliwatt. Okay, this is actually how most radio frequency equipment is measured as far as sensitivity goes, in dBm. So let's say we have an antenna that gets us a plus 5 dB gain. Okay, so if we have minus 124 here and plus 5, that means that our new value right here, by the time it gets there, is minus 119. We're just going to add and subtract. Okay, and we have, let's say, minus 10 dB in the cable. So if we have minus 119 and minus 10, that's minus 129 dBm. That's our signal strength.
Hey, Scott, where did you come up with the 124 dBm?
I made it up.
Okay, that's just random number. Okay.
It's if you measure it, it's the amount of energy that is in the air to be received. That's getting into the antenna.
Okay.
This is actually due to a whole bunch of different things. If you want to go one step further, you have a transmitter on the other side that has a transmit power up through cable, right? It's going up through cable, and then there's an antenna that it's transmitting through. But then you have this thing called path loss as it's traveling through space. And the path loss could be 130 dB or 140 dB. I mean, enormous amounts of loss. So that's where we're getting that. So I just happened to pick a number that is somewhat, some kind of appropriate to demonstrate a point. So let's say that our receiver has a sensitivity of minus 125 dBm. Is it going to receive that signal? Yes or no?
Yes.
The receiver, this is the lowest signal that it can possibly hear.
Oh, no.
No. Okay, so what if I take this signal, which is minus 129 here, and I put an amplifier right here and bump it up by 10?
Yep, that'd work now.
That would work. But what if the amplifier has a sensitivity of minus 125 dBm? In other words, if it's below 125, it can't even hear it enough to amplify it. And the answer is no, that doesn't work. The one thing you can do to fix this is you can take this amplifier and amplify it before you have a signal loss in the cable. You can put your amplifier up here. And this could be a 10 dB amplifier. And now instead of you had minus 125 dBm sensitivity, well, you're at minus 119. You're good there. Your new signal strength is minus 109 when it goes through the amplifier. And now, instead of minus 129, it's minus 119, and now you can hear your signal. So when people who work with, for instance, moon bounce and other weak signal modes put up amplifiers, they will typically put an amplifier all the way up at the antenna. Now, there's a corollary to this. Does anybody have a cable TV system? Does anybody have a dish network? Okay, they work the same way. Basically, you can't amplify what you can't hear. So, essentially, if you've got a cable TV network that looks like this, or a cable TV system that looks like this, and you put your amplifier all the way here at your box, that doesn't do any good because your amplifier can't hear what it can't amplify what it can't hear. So what they do is they add these little amplifier boxes way up here near the antenna or way over here at the beginning of the cable so that by the time it gets to your box, there's still enough signal left to actually hear it. So this is a cable TV system, and this is a satellite TV. This is exactly how those systems work. And when they come into your house and they say, oh yeah, I noticed that no wonder you're getting blocking of your picture. No wonder you can't get this channel. That's because the signal's not strong enough. What they do at that point is they start looking for the amplifier that failed and replace it. Or maybe they've got a section of cable up here that has a lot of loss, and they start replacing pieces of cable or connectors for that exact same reason. Maybe the system is such that it was not designed properly and there was no amplifier in there. And what they do is they go out to the box and they put a booster amplifier on the cable, and now you can watch your you can watch your channel again. See, you're learning stuff about stuff that isn't even ham radio, right? Okay. Which of the following is used to convert a signal from one frequency to another? We talked about that. That's called a mixer. A mixer is at the heart of a transverter. The name of a circuit that generates a signal at a specific frequency is called an oscillator. A simple oscillator is you take your speaker and a microphone and you put them next to each other and it goes. That's an oscillator. You don't intend it to be an oscillator, but that's what it is. And finally, the combination of speech with an RF carrier signal or any information with an RF carrier signal, we talked about it yesterday, that's called modulation. All right, 5-minute break, and then we're going to be on to systems, causes, and cures of common transmitter and receiver problems on page 87.
Any word on our balloon?
That is a great question. Let's go look. It's light out, and the last time one of these went up, it went up over Central Oregon, and it developed a hole, and it crashed to the ground. So, you know, it's experimental. So let's see. Any word on the balloon? Come on, baby. Oh, look at that. It's, no, still from last night. So, I guess we'll find out. If it wakes up this morning, we'll see where it is. It could also be that it's over a very, very unpopulated area, in which case it might be transmitting and there's nothing there to receive it. So keep the fingers crossed. You would hope that it would show up by now, but there's no guarantees. We actually launched one about a year and a half ago that went up. It made 2 full trips around Oregon. And then it got picked up and drawn all the way up over northern Canada, came down somewhere over Manitoba, made a few loops around the central United States. Over a period of 2 weeks, it came down into Alabama. We thought it was going to head out over the Atlantic, but it got sucked back over Texas, and we think it got knocked down in a thunderstorm. But it was just a 18-inch party balloon, and it went around the United States like for 2 weeks.
How do you send those up without interfering with aircraft?
There are requirements the same way that you will, that like if a balloon just gets up into the air, you know, people release balloons all the time. People accidentally release balloons all the time. There are stringent specifications for what you put up there, and basically anything that you put up has to be certified to be easily destroyed by an aircraft engine without damaging it.
Oh, okay.
So yeah, there are stringent requirements for meeting those specifications. And I mean, this is the whole thing. Let me show you what it looks like. What the hell's KB8 WB8 ELK transmitter? There. That's what it looks like. The whole thing weighs 8 grams, and that has a GPS, an environmental measurement package, and a 10 milliwatt transmitter in it. And the solar panels are, like a gram a piece, just floating off to the sides. So they're basic. So basically, there's no battery on board. When the sun goes down, the thing just floats around, and you hope that it wakes up in the morning.
That's very cool looking.
Some of them, if you get lucky, they can be airborne for months. If you look, there are actually some that are probably still up that have been up for months. And so long as because they're up so high, 10 milliwatts is still enough to be heard, 100 miles away. So long as there's a receiving station within 100 miles, you'll still see information from them. It's pretty cool.
Very cool.
All right, bathroom time. I'll be back. All right, ready to do this again?
Ready as we'll ever be.
Yes, okay. All right, so we are into symptoms, causes, and cures of common transmitter and receiver problems. Okay, so if we put out a signal, it is a signal that we are intending to put out, hopefully. If we're putting in a voice, for instance, into a transmitter that is a nice, clean voice, our goal is to get the same nice, clean voice coming out so that the person on the other end can understand what we're saying. Let's look at radio frequency interference. There are multiple different kinds of radio frequency interference. One is fundamental overload, which is basically there's just too much RF. It doesn't even matter if it's on the frequency we're listening to. There's just so much RF there that you can't hear anything. This is a very common problem when you have like a really cheap radio. We'll use the word Baofeng, not to knock Baofeng radios, but their filtering is somewhat minimal. And they have what I would call a glass jaw, which basically means, you know, they get hit in the chin and they fall apart. If they're in a high RF environment, let's say a city where there are a lot of different transmitters out there, even if they're not on the same frequency, they will become desensitized to the point where they don't really receive anything anymore. That's fundamental overload. Harmonics, a harmonic is a multiple of a frequency. So if you're transmitting a signal on 10 megahertz, you'll make harmonics on 20, 30, 40, 50, 60, 70, and they'll decay in amplitude, but they'll still be there. And then spurious emissions, which are a non-harmonically related frequency. For instance, a 10 megahertz transmitter, if it's not working properly, might put out a signal at 28 megahertz or 64 megahertz, someplace that it's not supposed to, but everything is built with amplify. You know, every amplifier somewhere in there has natural resonant frequencies, even if you don't, you know, even if you don't intend it to work in a certain way, you know. I can't change the note that this makes. There's nothing I can do about it unless I drain some of the coffee out of it. And even that doesn't change it a whole lot. I might try to make it oscillate at a different frequency or amplify signals at a different frequency, but that doesn't mean it's going to. So anyway, those are known as spurious emissions. So fundamental overload, harmonics, and spurious emissions can all cause radio frequency interference. Okay, if your neighbor tells you that your station's transmissions are interfering with their radio or TV, the first thing to do is check your own radio or TV and make sure that when you're tuned to the same channel, it doesn't do it to yours. If it does it to yours, you might have a problem with your transmitter. If you aren't affected by it and your neighbor's system is, it might not be you at all. Well, it might be that it's you, but it might be that the neighbor has a really cheap TV or radio. If that's the case, whose fault is it? If you're operating legally, it's their fault. Every piece of equipment that you buy, every cell phone, every iPad, every power supply will say part 15 on it. Okay, so part 97 is the rules that govern ham radio. Again, part 97. Part 15 is all the rules that govern things that may put out a signal and may be affected by a signal, but aren't intended to do that. That includes power supplies. It includes your computer. They'll all say complies with FCC Part 15, which basically means if I am transmitting a signal legally using my legal station that has been engineered to good amateur practice, you know, good engineering practice, I've done my due diligence, I know that it's working right, and every time I transmit, I shut off my neighbor's TV. That's not my fault, right? That means that your neighbor's TV is not really designed very well. Now, it doesn't mean you shouldn't help them, but it does mean that the problem is not yours. Again, you might want to be a good neighbor and help them out, but it's not your fault. What would be the first step to resolve non-fiber optic cable TV interference caused by your amateur radio transmissions? Those connectors have a way of coming loose, so make sure all the cable connectors are nice and tight. A broadcast AM or FM radio Why would it receive an amateur radio transmission unintentionally? That would be known as essentially fundamental overload. It's unable to reject strong signals outside of the AM or FM band. This actually I've noticed when I was driving past a really big AM station, and it didn't matter what my radio was tuned to, that's what I heard. Because there was so much signal there, it was just completely overloading my receiver. How can fundamental overload of a non-amateur radio or TV receiver by an amateur signal be reduced or eliminated? Well, this comes down to drawing the map. So here's the map. So here's my signal, and here's FM radio. So let's say that my signal right here is interfering with somebody's FM radio. They're listening for a channel. How would I block this signal out on their end? What would I use? It looks like this. What would that be called?
Filter.
That's a filter. Yes, there's that word again. That is a filter. So by installing a filter on their antenna, that would essentially block my signal from getting in. Okay, which of the following can reduce overload from a VHF transceiver by a nearby commercial FM station? Well, there's a couple ways to do it. So let's say that now this is the FM station, and I am the ham station, and so here's my 2-meter radio, and here's the FM station, except now we're going to make its signal super huge. What could I install on my station to make sure that it didn't get overwhelmed by that other station?
Your own filter?
Your own filter, that's right. Now, it can look like that. That would be a bandpass filter. The other thing it could be is to say, okay, well, I am actually going to allow everything except for that particular thing to get through, and this is known as a band reject filter. So essentially, we're going to be okay at these frequencies and okay at these frequencies, and we're going to notch out that filter. And it's also known as a notch filter. What should you do if something in your neighbor's home is causing interference to your station? Well, if it's a Part 15 device, it's their fault. So you really need to tell them, hey, you're not allowed to be using that because I have a legal station and you're interfering with me. It might be that you go through their house and try to figure out what it is by unplugging things and seeing when the problem goes away. And finally, making sure that, you did everything you could on your end. Now, here's another story. I have a story where I had a signal. I was on the 80-meter band, which covers 3.5 to 4 megahertz. And I heard an FM signal at 3.5 to 3 megahertz. Number one, there's no FM on that band. Not okay. Most of the time it was just a carrier, but sometimes it was a modulated carrier. And I could actually hear, if I tuned to FM, I could actually hear a voice. And it was definitely not a ham frequency. I mean, it was definitely not a ham radio. I thought, well, that's really weird. Why would it be there? And so I started walking around my neighborhood, and it got strongest about 3/4 of a mile from my house. And sometimes there was nothing there, and sometimes there was a voice there, and I thought I heard a name. And I asked my wife, and I said, do you know somebody named blah, blah, blah? Because I think they're broadcasting their telephone signals all over the neighborhood. Well, it turned out that back in about 1989, in her house, she had actually wanted up in this upstairs room to put a phone, but didn't want to run the phone cord. So what she did was she bought this device which connected to her phone and connected to the power cord, the power outlet, and modulated a signal on the house wiring, which went all around the house, using a modulated signal using FM
which at the other end would have an equal box, which would demodulate it and connect to a telephone. Okay, so that's fine. It was operating on 3.523 megahertz. It was running very, very low power, so technically it didn't have to be licensed. But what does every piece of wire have the possibility to turn into?
Antenna.
And any piece of wire, including your house wiring, can be a really good antenna. So what we found was that signal was propagating not only throughout her house, but it was also being radiated at 3.523 megahertz and sending her cordless phone signals, all her private conversations throughout the entire neighborhood. And I actually called her and had her listen to it, and she said, "Oh my God, I think I'm going to unplug that." And then she said, "Thank you for helping me find it. Would you like it?" I said, "Yes, I would." I can take it and make sure that nobody ever uses it again. So, okay, what can be your problem if you receive a report that your audio signal through an FM repeater is distorted or unintelligible? Okay, if your batteries are running low, your radio might not be at the right frequency. You could be in a bad spot, in which case you have destructive interference, and you might not have a strong enough signal to get into the repeater. And if your transmitter is off frequency, FM does not do well when your transmitter is off frequency. It sounds all distorted. RF feedback. If you have RF feedback, that's basically RF being picked up by your microphone cable. If that happens, your voice is going to sound all garbagey. Basically, bad, bad, bad. What do you do if you're told your FM handheld or mobile transceiver is over-deviating? Okay, so very often we will have something called a microphone gain control. And if we were to draw this map again, all right, we have a mic gain. So here's our center frequency. When we're using FM, our mic gain causes the frequency to deviate, as it's called. It's basically to change, to spread out from the center frequency as we talk. Typically, this is minus 5 kilohertz on one side and plus 5 kilohertz on the other side. Now, if your microphone is too hot and your radio does not have a control to control that, it might actually come all the way out here. Well, the receiving station is listening because it has a filter in this window. Well, if your signal is spreading out past that, what's going to happen to the signal that's spread out past it?
They hear it.
That's part of your voice. That's part of what you're saying. Well, all of a sudden it's not there anymore, which means that what's left is going to sound all distorted. This is basically called over-deviating. And since most handhelds don't have a microphone gain control anywhere, the way to reduce your signal is to take the microphone and just pull it away from your mouth. Move your face away from it. And that does the same thing as reducing the mic gain. Okay, next one. Using basic test instruments and doing soldering. Okay. Using a multimeter. Multimeter is good for measuring voltage and resistance. Voltmeter. A multimeter does that. Measures electric potential or electromotive force. That's called a voltmeter or voltage. How do you connect a voltmeter? So let's say that we wanted to have a battery here, and we wanted to measure the voltage of the battery. We would put it right here in parallel with the battery. Now, if we wanted to measure the current that was flowing, we would take it and do this. We'd take an ammeter and stick it in line with it. Now, let's say we didn't have the ability to actually break that line. What we could do is we could take a core, like a toroidal core that was in 2 halves, and snap it over that wire. And every wire that has current does what? Makes a what? Wire that's carrying current makes a magnetic field. So basically what this is an electromagnetic induction coil. It picks up the magnetic field and then says how much of a field am I using, how much of a field do I have, and then it has another transformer and it generates a current and a voltage out of it, and then it measures it and is able to measure the current indirectly. And that's actually known, instead of an ammeter, that's known as an induction ammeter, because it uses induction.
Is that those meters that kind of have the crab claw on the end?
Yep. That's actually, or sometimes we'll call it a clamp meter or a clamp-on meter. Okay, so a voltmeter goes in parallel, an ammeter goes in series. Okay, so what are ways to damage a meter? Okay, so these are ways to damage a meter. All right, the first thing is we have to draw what an ohm meter does. Okay, so we have an ohm meter. Everybody remember what Ohm's law is? E equals I times R. An ohm meter internally has a battery. And what it does, it also has an ammeter, and it basically puts a voltage across and creates a current and measures the current. And since it measures the current, well, then it can indirectly figure out, because it knows what the voltage was, it can figure out what the resistance was. Now, what do you notice is right up here, in that ohm meter, you have a battery, right? So what does that mean if you hook this up to a circuit where there's already a battery? What's going to happen to your measurement?
It's going to overload it.
Or it's just going to be wrong, right? You could actually damage the meter, or the result could just be totally wrong. So if you're measuring the resistance of something that's in a circuit, you have to disconnect it from the circuit. You have to actually break the circuit. In some cases, if it's on a circuit board, that means you actually have to unsolder something to measure it. Okay, what can damage a multimeter? Attempting to measure voltage when using the resistance setting. Well, yeah, that'll do it. And we can draw out why if we need to. When measuring high voltages, make sure the voltmeter and leads are rated for the voltages. So the reason that I bring this up is because everybody, I think, has been... I like Harbor Freight. Harbor Freight has its place, all right? Has anybody ever seen one of these?
I think I have 6 of those.
Yeah, sometimes they give them out for free. And whenever they give them out for free, I go and get one. And I usually donate it to my local club, right? Notice it says 7-function digital multimeter. It measures HFE, which is for transistors, diode checker, resistance. It'll measure up to 250 volts DC, 250 volts AC, which is pretty great, right? I've seen these that'll actually say 750 volts. Now, these are given away for free. Normally, they cost about $7. However, I can also go and buy one of these. Does anybody have one of these?
Yes.
I use one of these at work. This is rated for 1,000 volts. Its probes are rated for 1,000 volts. These also cost about $500 a piece. This costs about $5. This costs about $500. What is the difference? The difference is that this one, if you hook it up to a high voltage, stands a chance of blowing up, and this one will not blow up. So this one's also probably considerably more accurate than this is, but if you're just trying to measure something, 24 volts, I would feel fine using this. If you're trying to measure 480 volts, everybody uses these because they're typically not going to explode. So it's very important to make sure that the leads and the meter are really and truly rated for the voltage that you're actually measuring. And safety is really important because, again, a meter exploding in your hands is not a good thing. How is an ohmmeter connected to a component to measure its resistance? In parallel, once again, if we do an ohm meter, we have this internally, plus and minus, and here's an ammeter, and it goes like this. So basically, you just measure across the resistor. Now, let's say that you, over time, as you're taking a resistance measurement, it starts off, so here's time and here's your resistance. You see something that starts at 0 and goes like this. And it starts at 0 ohms and goes to basically infinity. This is the sign of a capacitor being charged up, because at first a capacitor will have nothing in it. It will be uncharged. And when you connect it, it'll just flow like crazy until it charges up. Well, once it starts to charge up, it slows down, and because it's basically measuring the current, as the current goes to 0, because the capacitor is charged, it says, oh, my resistance is now infinity. So a curve like that indicates that there's a large capacitor in the circuit. So the resistance increases with time. An instrument that's used to measure electric current is an ammeter. An ammeter is typically connected in series. If you're soldering something, do not use acid core solder. Acid core is really used for plumbing, and it will cause all kinds of damage to the circuit that you're actually trying to solder. A cold solder joint is going to be not shiny. It's going to be lumpy and rough, and basically you can have a solder joint that is mechanically solid but not electrically solid. And unfortunately what that means is if it gets jostled, all of a sudden it's not a good electrical connection either. So typically if that's going to happen, it's going to happen when you don't have a soldering iron handy and you can't fix anything. And then all of a sudden your equipment doesn't work anymore. So a good solder joint should look like a nice, clean volcano-looking thing without a real crater. It should be nice and shiny. And if you want to learn how to solder and you don't know how, soldering is a wonderful art to know. There are a lot of people who have spent a lot of time with a soldering iron in their hands, myself included, who would be more than happy to teach you. Operating procedures. What type of amateur station simultaneously retransmits the signal of another station? That would be known as a repeater. An amateur station that can automatically retransmit the signals of other amateur stations. Okay, so there are 3 of them. One is a repeater, which is typically a terrestrial antenna system and radio that has signals going in, and then it retransmits signals going out on a different frequency. So that's known as a repeater. An auxiliary station is basically like a forwarding station. So here's an auxiliary station on a mountaintop. And what an auxiliary station does is it picks up signals from typically one place and retransmits this, for instance, to another mountaintop. So that would be known as an auxiliary station. It's not really meant for individuals to use. And finally, if you're above 50 kilometers above the surface, you are technically in space. If you are in space, you are now a space station. And a space station is allowed to have a repeater on board and function as a repeater and retransmit signals. There is something out there called the ISS. The ISS is floating around at about 220 miles. And it has a repeater on board. So you send your signals up on UHF, and they come down on VHF. And that is actually known as mode UV transmission. They actually have a repeater on board. I actually talked to an astronaut about a month ago. It was very cool. To increase the range of a repeater system, some repeater operators link their repeaters with other repeaters. A linked repeater network is one where repeaters receiving signals are transmitted by other repeaters on the same network. So essentially that looks like this. So here's one, here's another one, here's another one. So if one of them receives a signal from somewhere, it is then sent across some backbone to all of them, and all of them retransmit it. We have one of these in Oregon called the Peak Radio System, which is about 50 linked repeaters going all the way from southern Washington to northern California and east to eastern Idaho, or eastern Oregon out to Idaho, northern Nevada. And what's cool about this is that if you have a handheld radio and you're like way down here somewhere, but you're within range of one of those repeaters, you can talk to anybody on any one of those other repeaters anywhere in the state. And it's a pretty big state in some areas that are fairly uninhabited. So you could be out hiking somewhere and still have coverage in an area where there will never be cell phone service. Okay, common repeater frequency offsets. Okay, there are 2 repeater frequency offsets that we have to remember. So on the 2 meter band, it's plus or minus, I don't know why it keeps drawing that, plus or minus 600 kilohertz. On the 70 centimeter band, so this is 144 to 148 megs, and this is 420 to 450 megahertz. It's plus or minus 5 megahertz. Those are our common repeater offsets. So if I had a repeater that was on 145.45 megahertz with a minus 600 kilohertz offset, I would be transmitting on 144.85 megahertz to be heard. If I were on 441.0 megahertz and it was a positive 5 megahertz offset, I would be transmitting on 446.0. Fairly straightforward. Okay, the thing that is the subaudible tone that might say with a PL of 123.0 hertz, that is known as a Ctcss, or private line, which is PL, which is a Motorola trademark. And that's known as Ctcss. If you know you should be able to be heard by a repeater, but for some reason they can't hear you, your PL could be wrong. Your offset could be wrong. You might be shifting in the wrong direction, in which case you're not getting on a signal. You're not on a frequency where anyone will hear you. You could also be using a DCS code that is wrong, or you might need to use a different DCS code. And that's, again, digital carrier squelch. Okay, a reverse function. So let's say I have my radio right here. My radio is set for 146.72 megahertz with a negative 600 kilohertz offset, which means that when I transmit on 146.12. So it might be helpful actually to have a reverse button. The reverse button temporarily switches those 2 frequencies. And what that allows me to do is, instead of listening here, it allows me to temporarily listen on this frequency, which basically gives me the ability to hear people in my local neighborhood who might be using that frequency. And what that allows me to do is say, oh, that person's really close. Maybe we should just talk, directly on a different frequency. Why would your FM audio be distorted on voice peaks? If you're talking too loudly, you are over deviating, and then when you're talking loudly, you could be pushing the signal too wide and you sound distorted. Okay, let's see. Now we're talking about appropriate way to break into another station's conversation if you know another station's talking. So the first one is say, okay, either they're talking or they're there. And let's see, is Vic here today? Okay, So the first thing to say is, let's say I want to call N7ABC, and I'm N7JI. That's it. That's what I do. N7ABC, N7JI. I use their call sign and then my own. If I want to say that I'm on frequency and listening, I say N7JI monitoring or listening. Now I don't call there's something that we have called CQ. We don't use CQ over a repeater because the assumption is if you picked a particular frequency where you know there's a repeater, you don't need to call CQ. CQ means you're looking for somebody to talk to with no expectation of there even being anyone on frequency. On a repeater, you'd say just your call sign and listening. Even easier, you could just say N7JI. Just give your call sign. And then if anybody hears you and wants to talk to you, they know you're there. And they'll just start talking. Okay. What is simplex? Simplex is the act of transmitting and receiving on the same frequency. If there's no repeater nearby, or you and another person are, let's say, a quarter mile apart, there's absolutely no reason, unless you absolutely need to tie up a repeater. In which case, you just could pick a simplex frequency and just talk directly. Good old walkie-talkie stuff. There is also a national simplex calling frequency. There's actually one on every FM band. On the 2 meter band, the frequency is 146.52 megahertz. On 70 centimeters, it's 446.000. This is the one that everybody should know. Everybody who has a radio that scans should have that programmed in. The reason being, you can go pretty much anywhere in North America and be on, even if it sounds like there's nobody there, you make a call for help or just for looking for somebody on 146.52 and you'll probably get an answer. Because by convention, everybody's listening on that frequency. Okay, so now we're into HF operation, which is high frequency. We're on page 97 of the book.
Real quick, could you repeat the 70?
446.
Thanks.
Yep. Okay, CQ. We use this on VHF if we're not expecting a repeater to be there. So if we're on simplex and you're looking for somebody to talk to, you could say CQ, CQ, N7JI, listening on 2 meters. If you're on the 20 meter band, you'd say CQ20, N7JI. Just basically, CQ means I'm looking for somebody. Literally, I seek you. It means calling anyone. Before calling CQ, the first thing, make sure you're first allowed to be on that frequency and that mode is authorized. You want to make sure by listening to make sure that there's nobody there. And then finally, you actually want to ask if the frequency is free. And the reason you ask if the frequency is free is because propagation is such that you might not be able to hear everybody. So let's say this is station A and station B and station C. Well, you are station A, and station B and C are having a long conversation. But conditions are such that you can be heard by station B, but not by station C. Well, station C has been chatting away for a few minutes, and you haven't heard anything, and then you just start calling. Well, station B, which can hear you, is busily listening to station C. And then all of a sudden you just started calling on a place where station B can suddenly hear you and you're interfering with station C. So the first thing you want to do is, because propagation is such that you might not be able to hear the other station, you want to ask if the frequency is available. You want to ask if you're going to interfere with anyone. How should you respond to a station calling CQ? If somebody says CQ, 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 this is, and they give their call sign, you'd basically say, that call sign, this is N7JI, over. You just basically tell them, hey, I heard you, just to make sure that there's no confusion. It's you I'm talking to, and here's my call. It's pretty straightforward. When you're making an on-the-air test transmission, let's say you're tuning up an amplifier, or you're tuning up an antenna tuner, you identify your station. You have to identify your station every 10 minutes and at the end of your transmissions. Those are the rules. A test transmission is no different than any other transmission. You have to identify it. Okay, on Morse code, we use a lot of Q signals. There are many Q signals. The reason we do it in Morse code is because to say I'm getting a lot of interference is a lot of letters. We can say QRM. Just 3 letters. There aren't that many Q words, especially words that start QR. So it's they were fairly available to use a letter that's, words that started with Q. QRM means I'm getting interference. It's man-made noise. QRN is natural noise. That would be static crashes. QSY means I want to change frequencies. There are other ones like QSL, which means you'll hear this a lot. Roger, I got it. QRX means hold on a minute. I mean, there are dozens and dozens of these. Most of them you'll never hear. Most of them you'll never have to hear. The big ones that you do need to know, you'll hear them all the time, are QRM and QSY. And these are the 2 that potentially could be on your exam as well. A band plan. Okay, so we were looking at the thing called the band plan. This is a band plan. So with a very few exceptions, a band plan is a voluntary method of keeping the peace by making sure that you don't end up with people on top of each other using different modes of operation. So there's nothing saying for sure legally that you cannot, on the 10-meter band, operate a certain mode in a certain place. However, the band plan says, by convention, these are Morse code frequencies. By convention, up here, these are FM frequencies. I think that one's actually a legal thing. But then in here, these are all voice frequencies. On the 2-meter band, you have a band plan. Notice you have Morse code only. That's actually specified by law. And then from 144.1 to 0.3, you have weak signal, which is basically single sideband. And then you have a mixture of different modes of operation. You have repeaters and you have simplex, indicated by different colors up here. These can actually vary a little bit from state to state as well, but these are the general rules are on this chart. And again, that's known as a band plan. And that's a voluntary guideline for using different modes within an amateur band, and it's to keep the peace. When 2 stations are on the same frequency, who has the right to the frequency?
The first one?
Yeah, unless the second one. Well, remember, conditions can change too. So it might be that the first one's getting weak, and then the second one is stronger. And so basically, they should just work it out. The easiest way to do it is, hey, sorry, I'm going to move up, or I'm going to move down in frequency. I'll pick another frequency. Because nobody owns a frequency. Even though some people may say they do, nobody owns a frequency. Okay, so now we're on to public service. ARES, A-R-E-S. That's the Amateur Radio Emergency Service. This is a volunteer organization that uses radios and licensed people and can provide emergency communications in times of emergency for the public service. Now, there's something that's very closely related to ARES, which is RACES, which is the Radio Amateur Civil Emergency Service. The only word in there that's really different is civil, right? That means that you basically have registered with a civil defense organization. It's run by your state or county government or local government instead of being a volunteer organization run by, for instance, the American Radio Relay League. It's run by your civil defense agency. They basically serve the same purpose. You can certainly belong to both of them. You can operate with both of them. They're specifically designed, specifically in support of civil defense communications. So what is RACES? It's a Part 97 amateur radio service. Part 97 is the FCC rules for ham radio for civil defense communications during national emergencies. They can both provide emergency communications. RACES is a little more codified because it's actually run by civil defense. Net control. Okay, so net control station has the ball. So we will create these things called nets. If you get active, you may participate in nets. A net is a good way to get used to structured communication. There's no reason you can't get on the radio and just have a general BSing conversation about whatever, right? I do it all the time. Just basically get on the air and talk to somebody about cooking or whatever it happens to be. A net is specifically set up for practicing how a network operates. So the way that a network operates is that there's a net control station known as net control. Net control typically has the ball and controls all the traffic that flows between people who are checked into the net. So the net control station will call the net to order and direct communications between stations checking in. All traffic goes through the net control station. If the net control station says, Station A, you're free to talk directly to Station B, then for that time, they're just talking, and when they're done, they transfer control back to net control. So essentially, it's a centralized network. Standard practice when participating in a net is to check in and remain checked in and remain quiet until you're asked to do something. So basically, you become a resource for net control. Now, it might be that, let's say that your network is distributed quite a bit, and you are, let's say, here's net control station, and here's net control station east. Net control has the ball. Net control is running things, but there are certain other stations, let's say A, B, and C, who can only be heard by the east station, by the east net control. And D, E, F, and G are all able to be talked to by net control. So it might be that net control receives from station D traffic, which is basically formalized information that is supposed to go to station B. There's message traffic to go from D to B. So basically that message traffic will go here, and net control station will say, hey, net control east, I have information for station B. Please take it. So they establish that communications, and then this station basically becomes net control and hands the information to B. Information says, yes, I got it, and then that information comes back to net control, at which point net control will say, station D, net control got your information. I'm resuming control. So basically, it's essentially a network, just like you think of as a network, except that it's people that are the network and moving traffic information back and forth. So traffic is formal information messages exchanged by net stations. Good traffic handling, that is to pass a message exactly as you received. So let's say that, oh, there's a good one. I always pick on somebody. Mark, I assume your last name's Hasse. Is it Haas?
Put the mic on here. Yes, it's Haas. Like
Haas. Okay, so there are three different ways to spell Haas. Well, you could do it H-O-S-S, you could do H-A-A-S, or you could do H-A-A-S-E. If I was trying to send message information across that says, hey, this person would like to send health and welfare status saying that they made it through the earthquake just fine, everything's okay, I would send traffic saying Mark Haas. Okay, but there's an ambiguity there. It could be M-A-R-K or M-A-R-C. So I would use my phonetics and say I spell Mike Alpha Romeo Kilo Haas Hotel Alpha Alpha Sierra Echo to eliminate any chance that there was any ambiguity. So using the phonetic alphabet is really important. And if you're on the air, you get used to using phonetics, which is another reason to practice. Information contained in the preamble of a formal traffic message is information needed to track the message. Basically, every time it moves from place to place, that preamble gets moved along with it, and it tells people where it came from and where it's going. A check in a radiogram header, kind of like a checksum, is an indication of how many words or how many bits are there. A check in a radiogram header is the number of words or word equivalents in the text portion of a message. Just a number, like 6.
Hey, Scott, real quick,
yeah.
is there a particular phonetic alphabet you have to use on ham, or you just want to make sure it's clear?
You want to make sure it's clear, but Alpha Bravo Charlie Delta Echo Foxtrot Golf Hotel India Juliet Kilo Lima Romeo Mike Kilo Lima Mike November Oscar Papa Quebec Romeo Sierra Tango Uniform Victor Whiskey X-Ray Yankee Zulu. If you know those are the international standard phonetic alphabet. You get used to that. Now, the only time that anyone has any real issues is, let's say they're a dispatcher for the police, right? Or they're in the military and they know multiple different sets. Sometimes those will bleed into each other.
See I did the old school back in the 80s, and since then I've used the civilian one. So I just didn't know if people would get upset if you used.
No, they'll understand. They'll understand, but more often, like sometimes I'll use an alternate one. If I'll use Japan if I'm talking to somebody in Japan and I want them to get it because they're used to hearing it. Something like that. Okay, when do FCC rules not apply to the operation of a station? The answer is they always apply. That's an easy one. Are amateur station control operators ever permitted to operate outside the frequency privileges of their license class? Okay, this always shows up on a test. I guarantee that this will be on your test. The answer is there are 2 reasons why you can operate outside of your privileges or outside of the ham bands altogether. Immediate safety of human life or protection of property. That's it. Life or property. The dam is about to break. You do whatever you can to get that message out. I'm trapped on a rooftop. Oh my God, please help me. I'm about to get washed away. That's an acceptable use. Now, if you were to say this actually recently happened, somebody actually got on a Forest Service fire department frequency and was trying to direct them to where this fire was near his house, and he was using the Forest Service frequencies. He actually just got fined $34,000 because there were other ways for him to do that. He just didn't. So that is an absolute last resort. Again, immediate safety of life or protection of property. If you can use the phone, if you can make a call out on the radio and have somebody make a call for you to the Forest Service, that's what you do. If it's not immediate. Okay, which amateurs may contact the space station, the International Space Station on the VHF bands? If you have now notice this says if you have a technician class or higher, you could actually have a novice class license, which is an old license that you can't even get anymore, but it didn't have VHF privileges. So if you have a novice, you can't. A technician class or higher, you can talk to the space station. A satellite operating in UV mode, that's UHF up and VHF down. The most common UHF bands to use for up are 70 centimeters up. Does everybody remember what UHF means? What frequency ranges? How many megahertz?
Was it 3 to 3?
What was it? For UHF.
30 to 300?
Nope, that's VHF.
300 to 3,000?
300 to 3,000 is UHF. VHF is 30
to 300.
Right. So if we're doing UHF up, that would be typically the 70 centimeter band uplink, and VHF down is typically the 2 meter band, which is 144 megahertz. And the more you do it, the easier it becomes. Okay, so that's mode UV. Now, while most satellites are FM, some use other modes. So what type of transmission is commonly used by satellites? You can have FM. The International Space Station uses FM. We can make satellites. Those who are doing ORSAT, you have multiple different modes, actually. There is also Morse code, which is CW. You can also do data, and you can also do single sideband. Those satellites are a little more complicated, but they work very well. The impact of using excessive radiated power on a satellite uplink is that you become the only thing that the satellite can hear, and nobody else can use it. So you block everybody else. An easy way to figure out if your satellite uplink is too loud or too quiet is to listen to yourself on the downlink, because you're hopefully going to be listening to yourself on the downlink anyway to hear what you sound like and hear what other people sound like. Your signal should be about the same strength as the beacon of the satellite. And a beacon sounds like essentially an indication of what the satellite is and what it's doing. It'll send information such as what the temperature is on board, what its call sign is, and things like that. So
how would you do that?
If it's Morse code, you just copy the code. If it's digital,
I'm sorry. If you're talking on the uplink,
yep.
How would you be listening on the downlink?
2 different radios.
Okay, gotcha.
And in fact, that's the easiest way to do it. To have 2 separate radios, because as it turns out, we're going to cover this. I might as well do it now. Why would you want to do that? Okay, so let's say that we're on the ground and we go uplink on 437.800. And we're listening to the downlink on 145.99. This is how the International Space Station works. All right. Now, when the space station is, let's say, coming toward you on a pass like this, and then going away from you on a pass, it's at about 220 miles up, moving at a speed of 17,000 miles an hour. Right? It's moving by pretty fast. It covers the entire horizon from horizon to horizon in about 10 minutes. It's moving pretty fast. Okay, but when it's directly overhead, is it moving toward you or away from you? In this direction. And the answer is neither. So when it's directly overhead, it's moving completely tangentially to you, which means that it's on the exact frequency that you think it's going to be. Now, has anyone ever heard a fire truck go by and notice that the frequency changes as it drives by, as it approaches you and then goes away? Well, we get the same thing. That's known as Doppler. As the ISS or any satellite is approaching you, its waves, which would normally be like this, are actually compressed. As it's moving away, its waves that are looking like this would be stretched, which means that the frequency as it's getting closer goes up, and the frequency as it's going away actually goes down, which means that your transmitted frequency, or the received frequency, changes, and your transmitted frequency changes. In order to get heard properly, you'd actually have to alter your transmit and receive frequencies. So that's why it's important to actually, and actually I think for this one it's the other way around. I think the uplink is 145.99. And the downlink on this one, it's a little weird, is 437.800. So you basically have to continually modify your receive frequency on the ISS. Not so much the uplink frequency, but the downlink frequency actually changes quite a bit. And you have to retune constantly in order to hear it properly. So this would actually be mode.
So if you talk to them, do you only?
Yeah, go ahead.
I'm sorry. I was going to ask you, when you talk to the ISS, since it's moving that fast and you're stationary, are you only getting out, hello, how are you, and then it's gone?
Pretty much, yeah.
Okay.
I made a contact with the ISS on over Field Day, which was end of June, And the contact lasted all of about 10 seconds. But it really happened. I got a confirmation card saying, "Congratulations, you've talked to Shel Lindgren." He was at the microphone. Normally, it's just operating as a repeater, but for that particular day, it was actually an astronaut sitting at the microphone. One of the highlights of my life. And again, this is known as that's Doppler. The need to actually change your received and transmit frequencies based on relative motion. Okay, a low Earth orbit satellite, LEO is low Earth orbit. A satellite beacon is a transmission from a satellite that contains status information on the satellite. It could also just be beep, 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 beep. When Sputnik was in space, that's actually all it did. It had a radio transmitter on board in 1957 that went beep, 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 and if you were tuned to that frequency, that's all you would hear. But that was a beacon. Space was pretty empty back then. Telemetry information transmitted by satellite beacons today, health and status of the satellite. That could be a call sign. That could be all systems okay. It could be what its location is. It could be what its onboard temperature and battery status are. It could be voice. It could be Morse code. It could be digital beacon. It could be a packet of information. Who can receive information from a telemetry from a space station, or in fact, who can listen to a space station? That would be anyone who has a receiver. So, I mean, you don't need a ham license to listen. Which of the following are provided by satellite tracking programs? Okay, so what I'm going to bring up is an AMSAT satellite tracker. Okay, AMSAT satellite tracker. AMSAT is the Amateur Satellite Corporation, and they deal with everything satellites. So if you're really interested in satellites, this is the one for the ISS. They have them for about 50 different satellites that are up there, maybe more, from all over the world. So notice we have the date and time, how long it's going to be up there, where it's going to show up in the sky based on where you are, and how high it's going to be. So clearly this 66-degree elevation would be a really good one, and that's coming up. Oh, look at that. That's going to be 8:20 tonight. That might actually be a visible pass. That might be something where we can actually see it pass overhead at sunset. Those are always cool. Which of the following are inputs to a satellite tracking program? Those are Keplerian elements, named for Johannes Kepler, who did lots of planetary motion math, predicted a lot of planetary orbits. Doppler shift is an observed change in signal frequency caused by relative motion between the satellite and an Earth station. So, if you're listening to a satellite passing overhead, as it's coming toward you, the frequency is higher. As it passes overhead, the frequency is lower. Spin fading of a satellite signal. As the satellite rotates, its antennas get closer and further, and sometimes they go actually behind the satellite. When they go behind the satellite, you can't hear them so well. So rotation of the satellite and its antennas causes fading. All right, operating activities. When we were listening to the SDR yesterday, we heard CQ contest, CQ contest. A contest is basically a scheduled time for people to be on the air using a given mode and set of frequencies, where it's essentially like everybody's going to be on. The intent being everybody's going to be on. It's a chance for everyone to make as many contacts in as many places as possible. That's called a contest. When you're doing a contest, the goal is to try to win because it's competitive. And because you're trying to win, everybody's trying to win, you're only sending as much information as is required for the contest. So it might be, my name is Scott, my favorite color is blue. All right, thanks, Scott. My name is Yvette, my favorite color is red. All right, thanks, Yvette. Next. And you're just moving on to the next. I got your information. Thank you. See you later. Next. A grid locator. One of the things that I sent everybody was, I believe, a grid map of the United States, which I can show right here. Okay, so this is a subset of the entire world. The entire world is split into little grid rectangles, which are 2 degrees in longitude by 1 degree in latitude, and they go all the way from the South Pole to the North Pole. 20 by 10 degree blocks are spelled out by letter, and then within each letter, you have number from 00 to 99. So everybody, you can look at this and figure out where you live and see what your grid is. I can say that I confidently live in Charlie November 84. The nice thing about having this grid system is that a lot of states, most states, are a lot bigger than just one grid, and it allows for a more a finer pointing of exactly where you are. So this is very, very helpful when it comes to operating with VHF and UHF when you're trying to point an antenna and all you know is that somebody is in Oregon. If you live in Washington State and you look at Oregon, Oregon looks pretty big, right? So which way do you point the antenna? Do you point it southwest or do you point it southeast? If you live in Maine and you're pointing to Oregon, you're only pointing one direction. But if you're nearby, like, you know, from Missouri to Kansas or from Oklahoma to Texas, that's a pretty big area. So it helps to know that, you know, you're pointing to somebody who's in Delta Mike 95. It makes it much easier to point. Okay, so that's a grid locator. Letter, number. Assigned to a geographic location. In order to locate sources of noise interference or jamming, we use something called radio direction finding. We also do a lot of practice when it comes to radio direction finding through these things called fox hunts. So here's our fox, and we don't exactly know where it is, but all we know is that we start here and we use our portable antenna system and we know that it's somewhere in this area. Then we might do another test and move over to here and find that it's somewhere in this area, and another test down here and find that it's in this area. Well, now we look at the intersection of all of those and we know that it's somewhere in that area. So then we get closer and we do it again. So that's known as direction finding, and fox hunting is a sport where you do direction finding and whoever finds the transmitter first wins the prize. Something that's useful for fox hunting or a hidden transmitter hunt is a directional antenna, usually a handheld directional antenna. Internet radio linking project. Like I said, there's a lot of hybridization between radio and networking these days. IRLP is a way to send data in the form of voice over the internet using voice over internet. And in fact, there is a red phone system that some people have come up with where they basically have created a public or a PBX or public broadcast exchange telephone system, and they have essentially over radio links set up a set of telephone numbers that don't require the internet at all, that just connect point to point over radio using your telephones. Because why not? So that's something called IRLP. Voice over Internet protocol is called VoIP. It's a method of delivering voice communications over the internet using digital techniques. The nice thing about digital things is that you can easily switch them and then turn them back into audio. So there's something called Echolink. Echolink is a system by which you can basically register your call sign with the Echolink people and then download an app to your phone. And once you've downloaded your app to your phone, you can basically use your telephone or your computer as a radio node and use it to connect to other repeaters that are on Echolink. So you provide your call sign and your proof of your license, they register you, and then once you have that, you can get on the radio using your phone. So let's say you're traveling and you want to talk to somebody on your local repeater who's mobile in their car, using their phone, using their radio, You basically dial up that repeater, and you are on the repeater transmitting signals back and forth, and you can call that person that you're talking to. Which of the following protocols enables an amateur station to transmit through a repeater without using a radio? Again, that's known as Echolink. How is over-the-air access to IRLP? That's Internet Radio Linking Protocol. Basically, once if I'm on the radio side and I want to use the internet, see these buttons down here? Back in the day, for the kiddies out there, we used to call these buttons touch tones. When you'd pick up a phone, you would actually hear doot, 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 and you get a series of tones. Once you key the radio by using the push-to-talk button, these buttons are actually used to transmit tones. Those tones are then used by the repeater to open up links to the internet. And then once you do that, you can actually, go from point to point and connect different systems together using those. So that's known as DTMF, or dual tone multi-frequency, also known as touch tones. An amateur radio station that connects other amateur stations to the internet is known as a gateway. So once you have established a gateway, you can get on the internet using your radio. All right. How about another 5-minute break? Ugh.
Please.
Any other questions?
What kind of little radio is that? You said it's a Yaesu?
I've got a Yaesu FT60 here. I've got an Anytone 878. This is a DMR handheld. I've got my Alinco DJ VX50, which is a dual band analog, but it's nice and waterproof. So, different radios for different purposes.
What happens if you win a contest?
Oh, well, you get a plaque. Sometimes you just get a piece of paper. So, usually there's no money or anything, but it's think of it as an opportunity to challenge other people and yourself. And for those of us who are competitive, I really like the competition. And more often than not, what I find is that, I'll make contact with okay, I've been on the air for 35 years, and okay, how many contacts have I made? Well, let's just see. Let me just sign in real quick. Here we go. I have actually registered in that time 30,000 plus contacts just not even using repeaters or anything like that I don't even bother to log. I've made 30,000 on the air contacts that I've even bothered to log. And how many of them are in the United States? Probably 2/3 of them. So let's say I enter a contest. Well, that's my chance. Let's say I enter sweepstakes, which is U.S. and Canada. And I've contacted every one of those 50 states, multiple times over, many times over. Now, what I get out of it is the fact that, okay, I'm starting all over again. During this day, let me see if I can work all 50. Let me see if I can work all 84 sections in the U.S. and Canada using either, a new antenna that I put together, or let's see if my brain is working better than it did last year. Let's see if my ability to copy code is better. Let's see if I can reduce my mistakes to a certain point. So, and the other thing is that, if you happen to have friends who are competitive as well, you can actually team up with them, either against them, or you can actually team up in the same location and work like a multi-operator kind of thing, where you have like 3 or 4 operators operating collaboratively from the same place, and then you enter as a different category. And of course, there are people who build superstations. So like if I go to K3LR, who are really serious about this stuff. Well, there's Tim. And let's see. Layout and design. So here's here's the layout of, you know, his antenna systems. This is for 160 meters. And you really can't see much up there, but here's the 160 meter 5-element vertical Yagi, right? That's an absurd antenna. That's 160 meters, which is, you know, AM radio bands, and he's got enough property to have 5 different antennas that are operating in conjunction with each other. Essentially, he's got a better signal, a better ability to put out a signal than most AM radio stations because he wanted to. You know, we have the opportunity to try things that we want to try. You know, our license gives us that ability. So, okay. Now, let's say that you're lucky enough to have a friend who is K3LR and is happy to invite you as a guest operator to operate his station because it's no fun doing it yourself, right? There's a lot of camaraderie that gets built out of that too. And everybody's on during a contest, you know. I mean, you block it off on your calendar that this weekend is contest weekend. And to say that, you know, there are a lot of contests to enter, this is the contest calendar just for this week around the world. That's just this week. So if we were to look at next week, we would see a different calendar. There are some things that are repeated every week. Here's a big one. Oh, North American Meteor Scatter Sprint. Apparently it has to do something. Oh, here's Worked All Europe. That's 48 hours long.
So I'm guessing you just like don't sleep that weekend?
Personally, I still have to sleep. I know people who'll stay up the whole time. If you're operating like a multi, where you have multiple operators and like 3 transmitters, let's say you get 8 people together, you operate in shifts. And what's kind of amazing is that, you know, like I'll enter a contest as a low power station from out here in Oregon, and if it's a domestic contest, I'll work, you know, I'll make like 250, 300 contacts. Some of the bigger stations, let's say over in Malta, there's a super station in Malta. There's another one in the Azores in the Atlantic Ocean. During that same contest, they'll make 12,000 contacts in a 24-hour period. Clearly, this is a different class of operation, right? And I would love to someday get to operate from there during that, but I don't know if I could handle it. The other thing that's nice about it is that when there's a station in one of those places, they're really fairly easy to contact. So if it's in a rare place, it gives you an opportunity to make contact with some rare places. And that's a whole other thing. That's known as DXing. And like I can bring that up. So here's LOTW. So here's my list of countries that I've managed to confirm contact with in my 35 years. Remembering that I've got 252 and there are 339 possible. So clearly I haven't gotten them all. So notice there's a whole bunch, like I've never contacted Algeria, Andaman and Nicobar. You learn a lot about geography, right? Andaman and Nicobar are their islands off the coast off of one of the Indian coasts. Angola, I'm kind of surprised about that one. Annobon, that's part of Equatorial Guinea. Aves, that's an island off the coast of Venezuela. Azerbaijan, just because it's hard to reach. Bahrain, I've heard Bahrain, I've never worked them. I've tried. Never even heard a station from Bhutan. Bouvet is uninhabited. Every 20 years, there's a group that tries to get to Bouvet. The closest we've gotten was a group that went about 3 years ago, and they made it to within a quarter mile of Bouvet Island. Does anyone know where Bouvet is? Ever heard of it? Here's where Bouvet is. Doesn't that look familiar? Here's what it looks like on satellite. And here's what it looks like where it really is. All right, so that is Bouvet Island. There are very few people who've managed to contact Bouvet Island because if you look at it, where do you go on Bouvet? Right? Completely uninhabited, covered with glaciers. Any guess how much it takes, how much money it costs to get to Bouvet? Let's hear it.
30,000.
A little low.
Low?
That's low. That's really low.
Oh my gosh.
Well, considering you're typically taking a dozen people with you, and tents and equipment and food and water and gasoline and generators, enough to survive there for 2 weeks, with all the clothing necessary to survive in the Antarctic. And you got to rent a boat because there's no other way to get there. All right, any guess how much it costs to get there?
100K?
$1 million?
$500,000 was the cost of the last expedition. All right, so they made it to Tierra del Fuego, and they had a boat, and they made it all the way to within a quarter mile of Bouvet. The weather was so bad that they couldn't go. They made it to within a quarter mile. They waited for days. The weather was so bad they couldn't go, and then one of the boat's engines went out. At that point, the captain said, "Sorry, guys, we're going to South Africa. We got close. Sorry. We'll try again another time if you want." They spent $500,000 trying to get there, and they never even got there. But, that's part of the adventure, right? Everybody wants them to try again. Takes a lot of time, takes a lot of coordination, and a lot of money. So that makes the fact that I was asked to go to Vanuatu seem not such a big deal, right? All right, any questions before we get going? This is going to be the last part. And for those of you who are in school, get your license and get on the high frequency bands, and you're going to learn a lot about geography. It will really help you. You will be able to blow people away with your knowledge of the map. If you want to work these places, you got to know where they are. Okay, what agency regulates and enforces the rules in the United States for the ham radio service? That's the FCC. The basis and purpose of the amateur radio service. This can actually be found on the FCC website as well as the ARRL website. There it is. We have 5 reasons to exist. Recognition and enhancement of the value of the amateur service to the public as a voluntary, non-commercial communication service. That means we don't make any money, especially for emergency communications. Continuation and extension of the amateur's proven ability to contribute to the advancement of the radio art. Radio is dead, right? Radio is old. This says that radio is not dead and radio is not old, because if this didn't have a radio in it, what would this thing be?
A brick.
It would be a brick. It'd be great for hammering nails in. So, encouragement and improvement of the amateur service through rules which provide for advancing skills in the communication and technical phases of the art. In other words, continue making improvements. Expansion of the existing reservoir within the amateur service of trained operators, technicians, and electronics experts. In other words, we are supposed to get better at what we do. We're supposed to find people who are better at this and are willing to learn, electronics experts. Everybody knows how to use a phone, but not that many people know what's actually inside it anymore. Everyone knows how to use a microwave, but for most people, that's just you put the water in and you push a button and it goes, right? Once you know the RF side of things, you understand. And finally, continuation and extension of the amateur's unique ability to enhance international goodwill. Even in times of war, even in times of disagreements between countries, even in times of, well, the Cold War, which went all the way through 1992. I have a stack of East German QSL cards this thick. I made contacts with East Germans all the time. Czechoslovakia, Poland, Hungary, Romania, all over the Soviet Union. I have lots and lots of cards from over there. So even if, our countries are not necessarily friendly, amateur radio is one of those things that is sort of outside of that. Okay, let's see. Definition of a beacon. A beacon is an amateur station transmitting communications for the purpose of observing propagation or related experimental activities. So a beacon goes beep, 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 and then it gives its call sign. And then maybe it changes its power level. Beep, 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 and then gives its call sign. The purpose being, okay, it's saying, I'm in this location, here's the signal. Tell me if you can hear it. And if you can hear it, that's good. That means that there's a path open between 2 points on the planet. A space station is any amateur station 50 kilometers or higher above the Earth's surface. That is the definition of a space station. When are you allowed to execute willful interference to other amateur stations, even if they're pissing you off a lot? And the answer is never. What we have the ability to do is use our finger and spin that frequency knob. If somebody's really annoying you, you can change the frequency. You can take your radio like this, and you have a frequency knob on it which you can adjust and tune to a different frequency. Which of the following entities recommends transmit and receive channels and other parameters for auxiliary and repeater stations? We have a volunteer frequency coordinator in every state and region in the United States, independent of where you live. There are a lot of repeaters. There are a lot of people who want repeaters. There are a lot of frequencies, but not that many frequencies that you can choose from, which means that there might not be a frequency available where you want it to be. So the volunteer frequency coordinator is selected by amateur radio operators whose stations are eligible to be repeater or auxiliary stations. So basically they elect the person to be the volunteer frequency coordinator, and that volunteer frequency coordinator then says, okay, you guys have given me the power. I'm going to decide who gets to use what frequency and how they use it. And I'm going to try to keep the peace and not make anybody unhappy. Of course, somebody always ends up unhappy, but they do their best. It's a volunteer job for okay, next one. Frequency allocations and power limits. This is one of those things that there is really no way to do other than memorizing it. I'm sorry, there's really no other way to do it. So you need to know what frequencies are available to you and how much power you're allowed to run and what modes you're allowed to run. So let's take a look at one. Okay, so which frequency is in the 6 meter band? So let's take a look at the 6 meter band. And what do we see? Oh shoot, sorry. I made my thing too small. Okay, there we go. The 6 meter band. Notice we've got 50 up to 54. Okay, so what they might do is try to trick you by saying, oh, which one is there? 222, 28, 52, or 49? Well, if we go through the math and say 300 divided by 6, well, that's 50. 49 is closer to 50 than 52.525. You need to know what the limits are and to know that the 6 meter band covers 50 to 54. So this is one of those places where there's no other way to do this other than memorization. Which amateur band includes 146.52? Well, there's 146. We're on the 2 meter band. On which HF bands does a technician class operator have phone privileges? You can look back at the chart and see that this says novice and technician. And phone is this hashed stuff right here, the little blue hash. You'll see that it's on the 10-meter band. Now you also have the green hash, but notice that says novice and technician CW. This is a, don't forget this, because you can actually operate Morse code on the 15-meter band and the 40-meter band and the 80-meter band. And my kid, my 14-year-old, had his technician license for 2 years, but also took a Morse code class. This is how we used to get on the air when we were first licensed instead of on voice. And he actually would come out to the station with me and operate on Morse code, because he could actually operate Morse code with a technician license on the 40-meter band and make contacts using his own call sign. He's since upgraded to general, so he doesn't have to do that anymore, but he could. Which of the following frequency ranges are available for phone operation by technician licensees? Again, this is just memorization, 28.3 to 28.5, and it's on the 10-meter band. Where can single sideband phone be used in amateur bands above 50 megahertz? Well, if you take a look at this, SSB, that would be the kind of greenish. Notice that there's green, there's green, there's green, there's green, there's green. Every band has at least some green. So there is a section of every band above 50 megahertz set aside for single sideband. And that's because it's used for weak signal work. What band segments are limited to Morse code only? Well, we can take a look at the band plan and see that Morse code only is CW, and there's only 3 that are allocated that way. Right here, and right here. So 1.25 and 2 meters and 6 meters. So of those choices, the ones that are selected are 50.0 to 50.1 and 144.0 to 144.1.
Hey, Scott.
Yes.
Yeah, I noticed that you said that novice was gone, but it's
not gone. Go ahead.
Yeah, the GMRS, I think it is, or a license where you spend $37 and you can get on the air. Is that the same thing, or?
Oh no, GMRS is GMRS.
Okay.
That uses 22 channels in UHF. And in fact, if we were to look at our frequency allocation chart, let's pull this up. I think I had it here. Let me unshare this and share this. Oh, it's the wrong one. Darn it. We have this one, I believe. There we go. Okay, can everybody see that horrible mess?
Oh, yeah.
Okay, here we go. So this is the whole frequency spectrum chart, and we're going to zoom in a little bit, if it lets me. And we're going to come down to here, and there's ISM, 120, 140. Okay, we're getting close, and it's going to be over here, and notice where it says land mobile right in here. Notice where it says land mobile. GMRS is somewhere right in here. What? Okay. All right, so land mobile and fixed, those are going to be your GMRS frequencies. Okay.
And Scott, just to be clear, so nobody gets in trouble, right? Those require a totally different license.
That's a totally different thing. Yeah, if you want a GMRS license, you send in $35, and the whole licensing scheme is different. It's $35, and you basically like license a family or group, and you have to renew it every so many years. I'm not exactly sure anymore. They've changed it.
I think it's 10 years.
Is it 10 years?
Yeah, I think so.
Right.
So the thing about GMRS is that there are repeaters, but typically they're not necessarily open repeaters. And but you can certainly use GMRS handhelds point to point. But then you're basically limited to the antennas you can use. You're limited to the power levels you can use. If it's local, it's great. Within a mile or two, it's great.
We use them for hunting.
Mm-hmm. Yeah, they definitely serve their purpose. Let's see, how can the 219 to 220 amateur band be used? And that is a kind of a special band. The 219 to 220 band is for fixed digital message forwarding systems only. And that sounds kind of weird because it is kind of weird. So that actually did not used to be a ham band, and it isn't even shown on that frequency chart that I brought up with you guys. And the reason that happened was because a long time ago, long time being like 15 years, UPS wanted to do something that was like a radio-based package tracking thing. So this band, which we used to call 220, is no longer 220. It's 222. Used to go from 220 up to 225. UPS said, we'll trade you 219 to 220 for 220 to 222. So we weren't using it a whole lot. So they said, okay, you hams can use 219 to 220, but it's only for message forwarding, basically bulletin boards. And then UPS repurposed the 220 to 222 band for their package tracking modules. Where somebody comes out and scans it and it sends it over the radio. I'm sure they've moved on from it since then. But that's why we have that weird thing. Why should you not set your transmit frequency to be exactly at the edge of a subband or amateur band? And that's because how much of your signal has to be within a ham band? Everyone? How much of your transmitted signal has to be within a ham band? That would be all of it. So if the frequency ends at, let's say, 14350, that's the upper edge of the ham band, and you're transmitting upper sideband and your signal looks like that, guess what? You are out of band. And you might get a nastygram saying, hey, you were observed being out of band. You have to make sure, because unlike, let's say, GMRS, where you bet a channel 1 and a 2 and a 3 and a 4 and a 5, and that's what you get to choose up to channel 22, we can go, for instance, anywhere between 14.000 and 14.350. We can tune anywhere. We are unique in that way. We do not have, with the exception of the 60 meter band, we do not have a channelized service. We may choose to do that, but we are not required to. We can tune to 14.17526.833. We can put our dial frequency there if we feel like it. Nobody else can do that. That also means that if we are able to tune, we need to know where we are not allowed to tune. So you want to make sure that your sidebands don't go outside of the band. You want to make sure that if your radio is off by 1 kilohertz, and this is really 14.349 or 14.351, that you're not transmitting out of band. And also, as your equipment warms up, it might drift a little bit. And what was in the band is now no longer in the band. So you want to leave yourself a little room.
How much room should we actually leave ourselves for this?
A kilohertz is usually good. So I mean, if you know that you're, and this is why it's important to know how wide a signal is. If you have if you have a signal that's 3 kilohertz above your carrier frequency, and it has to be below 14.350, you need to be at 14.347 or below. So I wouldn't go above 14.346, for instance, just to make sure. Every so often during a contest, you'll hear somebody who is on 14.349. And it's that they're maybe not paying attention, or they just don't care. They wanted an empty frequency. Well, it seems to me like they would not get a whole lot of replies either by people who know what they're doing. And I think that, in fact, is the case. On some bands, we are secondary operators and not primary operators, which means that somebody else is the boss. So if we take a look at this band, for instance, these bands, we will see that on the 70 centimeter band, we are actually secondary across the entire band. Notice this also says no 420 to 430 along the Canadian corridor. And that's because in Canada, hams aren't even allowed to use those frequencies. So if we're within 100 miles or so of Canada, we're not allowed to use those frequencies because we might interfere with their services, which aren't even hams. Similarly, if somebody is on, let's say, 435 and I have a repeater there and it's operating and it turns out it's interfering with, let's say, military operations, they can come on frequency and say, hey, you're interfering with the military, you need to turn it off. We're secondary, they're primary, we actually have to turn it off. On a lot of other bands, we're primary. Another one where we're secondary is this 60 meter band. Notice that it's channelized. The military operates here. And if they decide that they need us to be quiet, they can say, we're taking over the frequency, you guys need to move somewhere else because we're secondary. Okay, let's see. Except for some specific restrictions, this is another very good reason why we are in class. What is the maximum peak envelope power output for technician class operators above 30 megahertz with a very few exceptions? And that would be 1,500 watts. You can do a lot of damage with 1,500 watts of RF, which is why you're taking a class. On the HF band, segments, which again are like over here. In the blue and green hashed areas, you're allowed 200 watts of output power, which is actually more than I even have the capability of doing as an extra. I just don't own the equipment to run 200 watts. Now, in the olden days, when people used to buy tube equipment, a 200 watt transmitter was actually fairly commonplace. Anymore, you're basically looking at most equipment will transmit on HF at 100 watts peak, unless you buy or build an amplifier. Notice this actually says, let me make sure that it's right. Okay, maximum peak envelope power, that's your peak power for technician class operators, is in fact 200 watts on the HF bands. Okay, we're on to license classes. For which classes are new licenses available from the FCC? Okay, so this actually requires me to write something out. So there was a novice, a technician, a general, advanced, and an extra, going up in privileges. So the novice has not been available for about 20 years. Now, there are people who still have a novice license, which is why these caveats have to be thrown into these to these band privileges. Like a novice has access to HF, but not to anything on VHF except for the 1.25 meter band. There are still a lot of novice licenses out there. If you keep renewing your license, they'll keep giving you back your novice. There is no such thing as a new advanced class licensee either. Although if you have an advanced class license, you're still allowed to be advanced class. It's very close to an extra, except that typically you lack the bottom 25 kilohertz of a lot of segments. Well, it used to be also that the advanced class, the novice class was 5 words a minute of code, and the advanced class was 13 words a minute of code. To get a general, you needed to get 13 words a minute. Technician was 5 words a minute, and the extra class was 20 words a minute of code. So you actually had to prove that you could receive code at those speeds in order to pass those, in order to get those licenses. So advanced class was the highest that a lot of people went for that reason, because they just couldn't get 20 words a minute. So in about 25 years ago, the requirement to do anything above 5 words a minute went away, and then about 15 years ago, the 5 word a minute code requirement went away also. But you still have people who are grandfathered, and now what you're available to get is the technician and the general and the extra. And the whole thing has been reduced to 3 written exams. It used to be that there were 5 written exams and 3 code exams. Now it's just 3 written exams. The normal term for an FCC license is 10 years. How soon after passing the examination for your first license can you transmit on the bands? As soon as you appear in the FCC database. So once you're in the database, you're good to go. Now, when I say the FCC database, I'm talking about this. I think I opened it up. Here we go. Here's the FCC ULS, which is the Universal Licensing System. If I type in my call sign, I will see my entry, hopefully, for my license. See if it's awake on a Sunday. And there we go. And here's my license. Here's all my information from my license. It says I am active, which means my license is active, which means I can use it. If your license shows up in the database, you can use your license. If your license shows up as inactive for whatever reason, you are not allowed to use it. And it's really as simple as that. You won't even get anything in the mail anymore. We used to have to wait. I actually waited 6 weeks for my first license to show up in the mail. You don't have to wait. If it shows up in the database, you're good to go. And how many operator primary station license grants can be held by one person? That can be 1. In other words, you're only allowed to hold 1 license at a time. Now, you can also hold a GMRS license with a ham license, no problem. You're only allowed to have 1 ham license, though. Who can select a desired call sign under the vanity call sign rules? That would be anyone who wants to. So my call sign, N7JI, is a vanity call sign that I picked in 2000 because it was available and I liked it. My daughter is W7HER, and it also happens to be her initials, and she happens to be a female, so it's doubly appropriate. It happened to be available, so we went and grabbed it. My son is K7NAR. Those are his initials. My wife is K3LUX. Her name is Karen Lux. It's a 3 call, which you're allowed to get a call sign with a different number than the area you live in, but it seemed appropriate at the time because her last name is Lux, so that's her last name. We got it with her call sign. Any licensed amateur can apply for a vanity call sign. Now, what we have noticed, and what I have noticed, is that somebody will apply for a call sign that's like, let's see. Why is this doing this? R0BBY. And I know that the FCC gets a big kick out of applications like this, right? Why does the FCC get a big application out of a big kick out of applications like this?
I'm not sure.
Well, okay, it starts with an R, right? This indicates that the person doesn't understand how the call sign prefix allocations work in the world. The United States is assigned W, N, K, and AA through AL only. Right? Those are, every call sign in the United States must begin with something from those banks of call signs. So R, as it turns out, if you look at the international call sign allocation stuff, that belongs to Russia. And every so often, somebody will submit something to the FCC that is wildly inappropriate, and the FCC has no ability to hand out at all. So if you're going to ask for a vanity call sign, save yourself the embarrassment of doing that, and know that every call sign must begin with a W or an N or a K, or if you have an extra class license or you live in Alaska, AA through AL. So the other thing is that there are different lengths of call signs. Every American call sign has to have 1 number in it. And the class of call sign is laid out such that it is either a 1x3 or a 2x3 or a 2x2 or a 2x1 or a 1x2. It always has to have a number. That X indicates where the number is, and the numbers 1 and 3, for instance, indicate the number of letters before and after it. So a 1x3 would be like W1ABC. That would be a 1x3. Call signs of this layout can be applied for by anyone with any license class. You can do KA9ABC. That would be a 2x3. That could be applied for by anybody. A 2x2, for instance, KG7TX. That's only applicable for advanced and extra class. KA3D, that's extra class only. And I wouldn't do that. Can't do that. 1x2. K3MM. That's actually Tyler. He lives in Maryland. That's extra class only. So for all intents and purposes, these are extra class only. So if you want to apply for a call sign that's shorter than that, shorter than something like up here, so this would be technician and general. And also extra. You can also have that as an extra. You would want to upgrade to extra so you can get a shorter call sign. Okay, so how long is your okay? So which of the following is a valid call sign for a technician? The answer in this case would be KF1XXX because it's a 2x3, and it starts with the letter K, which means it's a US call sign. So that would be fine. The grace period for renewal if an amateur license expires is 2 years. If your amateur license has expired and is still within the grace period, can you operate? What will happen in the database? It will show as inactive. If it's inactive, the answer is no. You have to wait until the renewal has been processed. Once it's in the database and shows up as active, you're good to go. A club station. A club has to have 4 members to be a club. President, vice president, treasurer, secretary. Has to have 4 members, essentially 4 officers, to be a valid club. Once you're a valid club, you don't have to be affiliated with anyone. You just have to be 4 hams to be a valid club. You can apply for a club call sign. Which of the following, somebody was asking this yesterday, which of the following can result in revocation of a license or suspension of a license? If you don't give the FCC a valid call sign and they try to get a hold of you through the mail and it comes back as undeliverable, if they try a couple times, they can actually just cancel your license. Either you moved, they can't get a hold of you, or you just don't care anymore. So they will cancel your license. That's why for people who travel a lot, let's say you have an RV, if you have a mail forwarding service or a PO box somewhere, that's fine. It gets delivered. Eventually it'll make it to you. From what locations can an FCC licensed station transmit? That would be any boat or craft located in international waters that's documented and registered in the United States. So if it's American property, if it's American land, if it's got a U.S. flag on it, it's part of the United States. Your license is valid. You still need to ask the captain if you can use it, but you're legal to do it. Okay, things that are authorized and not authorized on the air. Okay. Things that are authorized and not authorized. So we are on page 115. Any such language is prohibited if it is obscene or indecent. There are some definitions as to what defines obscene and indecent. Basically, use your best judgment. If you wouldn't say it to an 8-year-old, probably don't say it on the air. When are you allowed to transmit music? When it's incidental to authorized retransmission of manned spacecraft communications. This came out of the Space Shuttle program when they used to do live rebroadcast of the Space Shuttle audio over the ham bands, which is perfectly fine. Except you remember when for those of us who are old enough, when they were doing the space shuttle and they'd do wake-up music, they would transmit that over the air. So if it's incidental to a spacecraft, that's a separate rule. They're allowed to actually transmit the wake-up music. That's the only time you'll hear music over the airwaves on the ham bands. When is it permissible to transmit messages encoded to obscure their meaning? Okay, for the most part, we are not allowed to do this, right? Ham radio is designed to be open and unencrypted. That includes, you know, speaking in words that are plain English but have some additional meaning, right? So we're not allowed to do that. The only time we're allowed to obscure a message's meaning is if we're controlling a space station or a remote control craft, because we don't want somebody to take it over and crash it. Who are we not allowed to talk to? If a country, okay, the International Telecommunications Union is a part of the United Nations. Every country is a member of the UN. They're all parties to the ITU. If a country says we don't want those American hams talking to our hams, then the United States will tell all of its hams, hey, you're not allowed to talk to whatever country. And there are no countries that we're on the list with. In what circumstances can you receive compensation for operating a station? All right, so somebody might buy you lunch or something if you're doing volunteering. You know, that's probably okay. Now, when are you actually able to receive a paycheck for being a ham? And that's if you're a teacher. If you're using it for classroom instruction, you're allowed to include it as part of your classroom instruction while still making your teacher's salary. When can hams use their station to notify other hams of the ability of equipment for sale or trade? So we're not allowed to run businesses. There are other services available for running businesses. If you got on the air on a local repeater, we have swap nets. Say, hey, I've got a Kenwood TM700 for sale, $100. You know, that's actually okay because it's ham related. It makes sense, and you're not doing it on a daily basis. If you're trying to run a business or you're just like advertising your pizza place, you know, there are other methods for doing that. What is broadcasting versus one-way transmissions? Okay. They're two different things. We don't broadcast. We do one-way transmissions or two-way transmissions. One-way transmission is information that is sent out for the general amateur community for which you have no expectation of response. That's one-way transmission. Broadcasting is for the general public. So it doesn't have anything to do with ham radio. So there's no broadcasting, but we are allowed to do one-way transmissions. So there are occasionally times when we are allowed to broadcast. And when, there's that thing again, you're allowed to broadcast for news gathering, program production, etc., when it relates to immediate safety of human life or protection of property. There's that thing again. If you see human life and protection of property, those are where the exceptions come in. So we can do broadcasting. So what are we allowed to talk about? Okay, as I've gotten older, I used to laugh at people a lot when I was on the air. And, you know, our communications were, hey, how's that homework going? Or, you know, like, you know, where are we gonna go this weekend? And I would hear older people talk about, oh, you know, I've got a doctor's appointment this week. Man, my back is hurting. And, oh, you know, I don't know when I'm going to get this knee replaced, but it's got to be soon because I just can't get around. Well, now I'm in my 50s, and I understand where they were coming from. Those are actually perfectly legal. And, you know, a lot of things are, you know, like, oh, well, I've got a doctor's appointment on Tuesday. I hear that a lot. Now I understand what they were talking about. So communications incidental to the purposes of the amateur radio service and remarks of a personal character. That's the kind of stuff we're allowed to talk about. We try to not talk about religion or politics or things that are divisive. You know, there are other means by which to do that. Everybody's got an opinion. We disagree on a lot of things, but radio is not one of those places where we typically air those grievances. Okay, control operator and control types. This is where we get into kind of the nitty-gritty of what is what on the air when you're operating. A control operator is the person responsible for what is coming out of that station. An amateur radio station is a pile of equipment, which could be as simple as a single transmitter, or it could be an entire station. Basically, a station is a collection of equipment that can put out a signal. A control operator is the person responsible for what comes out of the station. So, I am, in this case, the control operator of this station. I have my hand on the equipment. I'm responsible for what comes out of it. If I turn the power on and I go to a particular channel, November 7, Juliet, India, testing. I am now the control operator, and that signal that went out of the station was my responsibility. Okay, so who does the FCC presume to be the control operator of a station? Assuming there's something in paperwork that says otherwise, that would be the station licensee. There are really two parts to a ham station. There's a station licensee, and let me see if I have a reference copy. Hopefully this pulls up quickly. Come on. So basically there's an operator license and a station license. In some cases, if you're basically an individual, you are, oh, here we go, perfect. Let me unshare that and share this. This is what a license looks like. So it's an operator license and a station license. So this basically licenses my stuff, and it licenses me to use it. Now, if I were a club station is a station license without any operator privileges at all, because it's a pile of equipment. So it has a trustee who is responsible for it, but it has no privileges at all. So an unlicensed person cannot go willy-nilly into a club station and just start using it. There has to be a licensed person there. There always has to be somebody with a license. Okay. Who must designate the station control operator? That is the station licensee. If I'm the licensee of a station and somebody else walks in and I said, I'm going to go use the bathroom, you're the control operator now. I can assign somebody else to be the control operator. When the control operator is not the station licensee who's responsible for the proper operation, that is actually both of them, because it's my equipment and you're the one who let that signal get out of there. So it's my responsibility for the equipment screwing up, and it's your responsibility for the indecent transmission that was sent out or something like that. If a repeater, however, inadvertently transmits communications that violate the FCC rules, the most common of them is indecent stuff. Somebody will think it's funny to hop on a repeater and curse a few times. As a repeater owner, I'm not responsible for that, right? I might have a moral responsibility to try to shut it down and to try to figure out who it is, but ultimately the person who's violating the law is the person who keyed up their radio and transmitted that over the air. So that's the control operator of the originating station. So when can a technician class licensee be the control operator of a station operating as an extra class license? And the answer is never. Now, I think the rule might be a little different if you were to say that there was like immediate safety of life and property. Maybe then, but really the answer is at no time. So when can who may be the control operator of a station communicating through an amateur satellite or space station? If you're allowed to transmit on an uplink frequency and somebody is, let's say that there's a repeater on the space station that's transmitting your signal back on a frequency that you have no privileges on, That might sound kind of weird, but they're the ones who moved your signal, not you. So then it's okay. Basically, if you're allowed to transmit on a certain frequency, even if that signal's being moved somewhere else, it's okay. The control point. Okay. This is the control point of my station. Everybody see my handheld radio? Right here. This is the control point. This is the point from which I am obtaining local control. So this would be local control, and this is the control point, the push to talk button. Remote control would be operating a station over the internet. That would be, for instance, I have a computer upstairs at my station, or my radio is essentially a computer itself, and I'm using the internet to connect to that radio. So I'm operating my station remotely. There's a lot of remote operation that goes on now for people who, let's say, live in Florida during the winter but have equipment in Minnesota and don't want to be there. What's required for remote control operation? The control operator has to be at the control point, which means sitting at the remote computer. The control operator is always required to be there, so if the person walks away, they're supposed to turn off the equipment. And the control operator indirectly manipulates the controls. You're using the computer. And automatic control. What is an example of automatic control? Again, there's an auxiliary station, there's a space station, and there's a repeater. And the only one here that's correct is the repeater. Okay, station ID and repeaters and third-party communications. Okay, we're on 121. You have to transmit your call sign at the end of each contact, not at the beginning. You don't actually have to give your call sign at the beginning. You have to give it at the end and every 10 minutes during. So you have a little 10-minute timer going on in your head. Every 10 minutes you give your call sign, and then when you sign off, you give your call sign again. The only time you're allowed to transmit without giving a call sign is when you're controlling model craft. Let's say you're running a drone. Let's say you have an RC car or an RC plane. Your transmitter is basically in a handheld box. You have to have your call sign and your name, call sign, and address on that box. That identifies your signal. What language can you use for identifying your station when operating on phone? Phone is another word for voice. In the United States, you have to use English. Now, interestingly, puedes hablar solo en español, pero cuando identificando November 7, Juliet, India, you have to give your call sign in English. When I got to operate in Chile, I could have conversations in English, but I still had to identify Noviembre 7J India Diagonal Charlie Echo 5. Because the rules were that you could have a conversation in any language you want, but you have to identify your station as that country says you have to. In the United States, you can have a discussion in Swedish. You still have to identify when you give your call sign in English. What method of call sign identification is required for a station transmitting phone? Well, you can say N7JI, or in the background, you can have a Morse code identifier that would go da-dit, da-da, da-dit, da-da, da-dit. And it can be in the background, so it wouldn't overlap. You'll hear that on a lot of repeaters, where they'll identify the repeater using Morse code. And it doesn't interfere with the voice. What do the FCC rules state regarding the use of phonetics? Phonetics are encouraged. They're not required, but they're really helpful because they remove a lot of ambiguity. When using a tactical call sign, let's say that you're helping out with a race. We do that around here. We do a 100-kilometer ultra marathon race. We give support for that. You have to give your call sign every 10 minutes and at the end. The rules are the rules. Now, you also have to say, let's say your ID is race headquarters, right? You can call yourself race headquarters. Is that an actual call sign? Yes or no? Nope. You can say aid station 6. You can say this is aid station 6 out. Every 10 minutes, you still have to give your official call sign, and you still have to do it at the end. The rules are the rules. Okay. When operating portable or mobile, you can assign a self-assigned indicator like /3 or /QRP or /mobile. So there are 3 different words that you can use to identify a self-assigned indicator. Slash, slant, or stroke. And all of those mean a slash sign. So if I wanted to be /QRP, which means I'm low power, I could say that I'm N7JI /QRP. It's okay to do that. Now, if I were to say that I were operating in another country, I would be CE5/N7JI. That actually identifies in Chile the call sign that I have to use. This is actually different because that actually is my official call sign. This one up top is a self-identified thing. So the rules are different. Okay.
Can we go back to the race for a minute?
What?
Can we go back to the race for a minute?
Sure, because it's something that a lot of us are going to be doing probably.
So if we're just listening to the race go on and hopefully everybody's safe and nobody needs to announce anything, are we still identifying ourselves even though we're basically just monitoring?
The rules say you have to give your call sign when you're operating every 10 minutes and at the end. If you don't have anything happening for an hour, you don't have to do anything.
So I guess I need to understand operating. If I'm not pushing
if
the
you're
top
not
button,
transmitting a signal, you're not there. If you're not transmitting a signal, you don't have to identify it.
That's what I need. Thank you.
Third party. Okay, so if you think about a conversation on the air, there are really 2 parties in every two-way conversation. So here's number 1, here's number 2. Number 1 and the 2 are having a conversation back and forth. A third party could be a third party that joins into the conversation. Now, there's no saying that the third party actually has to be in a different place. Third party could be right here. So in this particular case, the third party could actually be giving information to the first party and saying, hey, can you tell number 2 that I said this? That would be a third party message. Depending on what you're doing, that is either legal or not legal. It depends where station 1 is and where station 2 is. If station 1 and station 2 are in countries where a third-party agreement is legal, then it's perfectly fine to do. And in fact, if that's the case, then there could be another third party here, which could be right here. And in fact, you can let them just talk on the air using your privileges and license. You're still responsible, but if you have a third-party agreement, you can actually pass information or let them pass it themselves using your 2 call signs. This is how we do, for instance, museum stations when we get little kids on the air. When they talk to a licensed ham, or if we have 2 different museum stations and we have 2 different kids, or let's say the Boy Scout stuff, where we have 2 different stations and we have 2 unlicensed scouts in 2 different places talk to each other. This is how we let them do that, using third-party operation. In the United States, you're always allowed to do third-party agreement between people. Canada, same thing. So between the US and Canada, no problem. If it's any other country, the rule of thumb is go check the list. And you go to the ARRL and you look up third party. And you look up all the list of all the countries and all the call signs which we have third party agreements. Sometimes we do, sometimes we don't. So check the list. Okay. And finally, if the FCC comes knocking at your door and says, I need to inspect your equipment, you have to let them in. They typically don't do that. But if they think that you have something malfunctioning, there was actually recently a station, who was a ham station, believe it or not, in Colorado, that was being operated remotely by the owner, who I believe was in New Mexico. and something malfunctioned, and that equipment was transmitting a carrier signal for a week on 7.033 megahertz, causing lots of interference. He actually got in trouble for that. The FCC, after lots of complaints, tracked him down. He had no reason to think that anything was happening. And the FCC actually went to his residence and found the malfunctioning transmitter and told him, hey, you know, you've got a fine for this. So, yeah, the FCC is going to, if you're causing interference, the FCC, if it gets bad enough, will go and find it. You don't want that to happen. All right. We have finished the entire thing, and we are right on time. Amazingly. And I know we've got lots of questions. And we're going to, I think exams start, if I'm not mistaken, around 1 o'clock. So I am apparently responsible for handling the scheduling and phone calls. So I have a list of phone calls that I've gotten, or from phone numbers. Let me look and see from JD. And on the list, let's see. I want to make sure that I've got everybody. Let's see, is Jessica Dean here?
Yeah, I'm right here.
Okay, did you get a message from JD and take care of whatever it is he was asking?
Yes, I just had to do step 2, and I did that this morning.
Oh, good. Okay. Let me take a look and see. He wants me to handle. Okay. So far, the list that he sent me was Calvin Baines, Joel Bryant, Tristan Crocker, Jessica Dean, Hiram Lewis, Nicole Lozier, Anna, Yvette, Amanda, Sharon, Shannon, and Jarrett. And that was as of yesterday. So, is there anybody who didn't get their name called who has actually signed up who I need to take a note of? Okay, so, well, I guess that's good. So let's see. As of right now, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. Let me just look at my let me just look at the session and see how many we've got scheduled. And we have 12. Okay. So, is there anybody who, I believe it starts at 1 o'clock. I show it starting at 1 o'clock, our time. So is there anybody who needs to go earlier or needs to go later? And speak now or forever hold your peace, because then I'll just start calling people randomly. Okay, I don't hear anything. All right, so I think I'll just start calling people randomly when the time comes then. And those phone numbers that you listed, just be ready to answer it. And when it comes time, what we're going to end up with, I'll probably send you an email as well, which has a link. And you're going to end up connecting with 2 devices. One of them is a laptop that you're going to take the exam on with a webcam, or a computer with a webcam. And the other one is a secondary camera system, which is either another computer, or it could be an iPad, or it could be, I guess, an iPod, or it could be an iPhone, or it could be an Android, or whatever it happens to be, that you're going to join us. You're going to join Zoom twice. And the first one is going to be with audio and with video. And the second device is going to be with video only. So we don't want audio, or else we're going to have horrible echoes and feedback. So that second device, when you connect, you're going to connect without any audio. And then we'll just basically get you set up to take the exam. We've got a really good technical team. And we'll set up to get you set up on the exam.tools website, which is where you're going to take the test. And we'll make sure that there's nothing on the ceiling, nothing on the floor. So when you probably saw it in the notes that you got, but when you go to take an exam, it's really important to be in a room where you're not going to get disturbed. There's not going to be anyone that comes in A door that can lock is really helpful. Some people take their exam in a bathroom because they can lock the door and they know it's quiet. And so if you if you do have to, here's the other thing: if you have to get up and go to the bathroom in the middle of the exam, we have to stop it and start it again. Now, I don't know what that means if you're already sitting on the toilet. I've never had that come up, but that would be something that might not be a bad thing. I've never thought of that before, actually. I have no filter. Anyway, if anybody else has any other comments or questions or thoughts or anything, now is a good time to air them. We got everybody here, and if you're thinking that there's a question, there's probably other people who are thinking the same thing.
Scott, I'm going to take off, but I sure appreciate your time doing this.
Well, I thank you for coming, and thanks for letting me use your name. Like I said, there's an example in every class. So.
I'm having issues with decibels still.
With what? Decibels?
Decibels.
Okay, what do you want to see?
For some odd reason, I can't seem to get the breakdown of them, how it moves from one to another and how many decibels it moves down, or how to calculate all that.
Okay, so this is okay. So what we're going to do is go back to an exponential or logarithmic thing. So we're going to start by saying here's our 10, all right? And everything comes back to the number 10, right? Number 10 is the most important thing. So if I have 10 times 10, that's 100. The question then is, what power did 10 have to be raised to get 100?
2.
Okay, so that's 10 squared. Okay, so now what I have is this exponent, which I had to raise 10 to get it. How about if I went to 1,000? What would I have to be 10 raised to what power? That would be 10 to the third. Okay, so now the decibels is just basically an easy way of explaining what that exponent is. So if I did this number, for instance, if I did 100,000, that's 10 to the what power?
5.
That would be 5, right? So that is actually the number of bells, right? Except that we're doing decibels, which is tenths by definition. So it's a decibel. So in other words, 5 whole things is equal to 50 tenths. So that would be 50 decibels. So the thing is with decibels, it's always compared to something else. So let's say that we have a starting point and an ending point, and the starting point is 1, and the ending point is 100,000. The question really is, we are now looking at something that is 10,000 times bigger, right? Everyone agrees? 10,000 is 10,000 times bigger than 1, right? Okay, but we want to know, so that's 10,000 times. We want to know, for shorthand's sake, if I were to take 10 to the somethingth power to get 10,000, what would that number be?
4.
That would be 4. All right, so that is 4 bells, which is the same as 40 decibels. So that would be an increase of 40 decibels. And we'd write that as 40 dB. Now, the other thing that's important to note is if I were to write 10 to the something is equal to 2, right? This actually is about 0.3, right? 10 to the about 0.3 power is 2. Right? So that's in bells. So how many tenths are there in 0.3? There's 3.
3.
That's 3 dB. So 2 times is 3 dB. And similarly, if I were to shrink the number at the same rate, I would say, okay, if I compare a starting point of 10,000 and an ending point of 1, that is 0.0001. And if I say 10 to the what power is 0.0001. By convention, that's -4. That's -4 bells. And now I have to convert to decibels, which means I have to multiply that by 10. So that's -40 dB. So a reduction of power by 1/10,000th, going from the starting point to 1/10,000th, is a change of -40 decibels. It's a convenient way of displaying big things because we're looking at the exponent. Does that make sense? I can't, you're still muted. Oh.
I'm just going to have to hope that the whole test doesn't involve too many.
At most you'll see one, but tell me what doesn't make sense.
I'm having a hard time linking it all together. Like when they say that there's been a change of, say, 124 decibels.
Yeah,
it's
okay.
gone down, whatever.
Okay, well, let's just do that. Let's say it's a -120, let's say -123 decibels. Okay? Well, the question is, now let's go the other way. It's 10. This is in decibels. We have to convert this, right? So it's -12.3 bells. So it's 10 to the -12.3 power. You can do that on the calculator. In fact, I'll pull up my calculator and do it now. And let's see, switch minus. Where's my plus minus? There it is. And 10 to the x, and I get 0.5, or sorry, I take that back. And I get 5.01, which I'll just say 5 times 10 to the -13th. And the reason, okay, well, here's the other thing that may be getting you. You ready? Why can we add, let's say we have 30 decibels and 20 decibels and get 50 decibels? Right? That's actually really important to understand. And what we have to do that is go back to the derivation. Okay? We know that if we have 30 decibels, that is 10 to the third power. And if we have 20 decibels, that's 10 to the second power. So if I have the same base and I multiply things together, what do I do with the exponent?
You just add them together.
Add them together. And there's the 5. So that's why 30 dB and 20 dB is 50. It's just simple addition. And again, that makes it really easy to work with because we're dealing with exponents. And exponents are much easier to deal with than to say, okay, well, I can guarantee that these things will give you the same number. Ready? 0.007 times 11.39. All right? I can guarantee you that if I multiply those out, 0.007 times 11.39, I get 0.07973. All right, now if I convert it to decibels, instead, I'm going to take 0.007. Okay, so 10 to the something is 0.007. So that's log base 10. I get -2.155. So I'm going to move it 1 decimal place because it's -21.55 dB. And now 11.39, I'm going to take the log of that, and I get that is 10.565 dB. Now, I can just add those together. right? Let's say that I had a loss that was there and a gain that was there. So I have minus 21, 0 minus 21.55 plus 10.57. I get negative 10.98 dB. Okay, which is the same as minus 1.098 bells. And then I would do 10 to the minus 1.098 and see what that gives me. And I get 0.0798, which is the same answer, isn't it? I get the exact same answer, except I didn't have to deal with this and this. Okay, well, that's not all that hard, but let's say that the numbers that I dealt with were 0.00000000062, and this number was 0.000000984. Right? Why should I have to deal with all those decimal points? I mean, there's so many decimal places in there that that number is going to be infinitesimally small. So this is it's really just a shorthand method of doing the math. I mean, I can say that, okay, well, let's see. You know, I don't even want to multiply them together, but I will. 0.00000000062 times 0.00000000984. Okay, I get 0.00000000000. I'm losing track. 61008. Right? Look at all those zeros. Right? That's a pain in the neck to deal with. But what I can do is I can say, what is 10 to the something gives me that first number. Right? So I'm going to take 0.00000000062, and I'm going to take the log of that. Now I'm going to raise that. Okay. Let's see. Times 10. Okay, 0.000. And I'm going to take I'm going to raise that. There we go. I get negative 9.2. So 10 to the negative 9.2 gives me that. So which means I have minus 92 dB. Okay? Which is easier to keep track of, that or that?
You can't just go 6.2 times 10 to the negative 11.
You could, but let's say that you then have an antenna that is then rated in decibels. Or decibels are a common language. Let's say that the gain is 7 dB. Then you'd have to convert that and then multiply everything together. So yeah, you can still do that. But here's 0.00000000984. And we're going to the log of that. We're going to raise that. 0.000000984. I got negative 8.0. So that's negative 8.007. So that's negative 80 dB. Okay, so if I have those two things, I just get negative 172 dB.
I think I'm just going to memorize the 3 questions for decibels.
Yeah, well, but you know what? Decibels come into play everywhere, because if you look at how cables are rated, if you look at power output levels, dBm. If you look at antenna gains, everything is rated in decibels. This is the common language of figuring out what a system does, because it works for every component. It works with power gain from an amplifier. It works with antenna cable loss. It works for a preamplifier. It works for signal path loss between 2 points. That could be negative 140 dB. Everything is normalized, if you want to think of it that way, to decibels. So either you can fight it or you can accept it.
I can accept it. It just ain't getting through my filter for some reason.
But you know what? If you start using it, then it'll start to make sense. All you have to remember is that you just have to look at all the ratings. You look at, for instance, if you look at, here we go. Let's go to Sherwood Engineering. Okay, Sherwood Engineering, receiver test data. Okay. This is a rating of how equipment does. Notice this. Decibels, 100 kilohertz blocking, 147 dB. Dynamic range, 110 dB. Dynamic range, 110 dB. Filter ultimate rejection, 115. So basically everything in the RF world is normalized to decibels. Because the numbers, like, okay, you think about it. Okay, you can say 115 dB, right? That's basically 10 to the 11.5 power. Right? Essentially, that's all it really means. But it's important to note that 100 compared to 110, that's a big difference. That's an entire, because that's 11th power versus 10th power. That's 10 times better. If this was 120, that'd be another 10 times better. So that's why it gets normalized. It just makes it a lot easier to compare things. It makes it a lot easier to compare different components that have performance.
Well, with any luck, there's an app for that.
Well, yeah, I mean, but the thing is, that's how everybody publishes things. If we look at, like, let's say you look at this and you say dB loss for cable. You look back at this diagram. I mean, this is how manufacturers test and specify their cable losses. And what's nice about it is that it's per 100 feet. If you have 200 feet, you just double it. If you have 600 feet, you just multiply it by 6. It takes care of all the powers of 10 for you. It takes care of handling the really big numbers and all the exponents for you. So it's a very convenient shorthand. But really, the only things you have to remember, 10 times is 10 dB, and 2 times is about 3 dB. Those are the only ones that I actually still know. And you can basically, work almost anything into something that's approximate. If I have a gain of 18 dB, well, that's 10 plus 3 plus 3 plus 2. That's a little less. So this is 10 times 2 times 2 times, I don't know, maybe 1.5. So that's like 40 times 1.5 is about 60 times. So it's really, really good for, just having these two values, 10 and 2, 10 and 3 dB. You can approximate a lot of things using those two numbers. All right, any other questions?
Yeah, I had a quick question with the exam.
Yeah.
So from what I'm understanding, the call will help to set up, and then at 1 the exam is taken?
Well, we'll just call you, and basically we'll figure it all out at that point.
Okay, with time scheduling.
Yeah, I mean, unless you need to go early and to say, I need to go early, please call me first. If anyone needs that, tell me. But you know, the time that we have blocked out is 1 to 4. I doubt that it will take that much time for anybody. I mean, a lot of it comes down to how well prepared individuals are, but we have a lot of examiners, I think, for this one. So we can probably handle 4 people at the same time.
Okay, sounds good.
How has everybody been doing on their practice tests?
I was actually in the middle of taking a practice test, and I'm wondering if I could be scheduled later, because I haven't even finished the practice test.
Okay. I will put you on. I'll make a note. And
please and thank you.
Yep, later. Okay.
Thanks.
Mm-hmm.
I want to say thanks for everything. I'm not taking that test this time. It's news to me.
Okay.
But I intend to be ready to take the test the next time it's offered.
No,
so
well, when you say the next time it's offered, what do you mean?
I think it's like 6 months out or so.
No.
Where
are you looking?
That's from Don. Or somebody, I don't know.
Okay, that's very, very wrong. Let's get this hammered out right now. All right. So if you start looking at taking exams, I want everybody to look at this right here. This is, and I'm going to share my, let's see. Here. All right. So I'm going to share my screen right here. And let me go back to that. And if you think you have to wait to take an exam, you're very, 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 very mistaken.
Okay.
So this right here, this is our schedule for the Anchorage group. Do you see what I see?
I see a lot of opportunities.
There's an exam every day except Sundays, just with this one group. And Anchorage ARC is one of 14 groups that gives tests.
Okay.
So who told you that you have to wait 6 months?
I think I heard it when I was at the Ham Club picnic or something. It was just general talk.
Well, maybe they only give in-person exams every 6 months.
Okay.
But yeah, I mean, if you're ready in 3 days, you schedule an exam and you take it in 3 days.
That I will not be ready that soon, but
if you're ready in a week or 2 weeks, whenever you're ready, you schedule an exam and you just go and do it.
Good.
Yeah.
All right. It's good to know that.
Yeah. It used to be a case where you used to have to wait a really long time. Like you'd have to go to the FCC office. Ask anyone who's had their license for 50 years and ask them how they did it. They had to actually make a 200-mile drive to the nearest FCC office on a day picked by the FCC and when they were convenient for the FCC to do it. And if they failed, they had to wait until the next time it was given.
Okay, wow. Yes. Well, that is good too. It affects my studying plan and my test taking plan.
Absolutely.
So,
yeah, you have an almost unlimited supply of choices for taking a test.
Okay. Well, your program has been excellent.
Thank you.
Yeah, it really has. And I want to thank you. And until next time.
Thank you all for, for coming out and I personally, I can't think of a better way to spend a 100-degree weekend here. So
Hey, Scott.
Yeah.
Just kind of building into the last question that came up. For those of us that don't have webcams and that kind of stuff, is there a central repository for test dates, or do you have to go to each individual hand club to try and find when they're doing their tests?
Well, the one way to do it, where do you live?
I'm in Arizona, and I'll actually be out of state for my local ham club. And I know there's a bunch of different clubs around, but I was wondering if anyone just put together a database of, hey, these are the test dates somewhere around this major metropolitan area.
So if you go to the ARRL website and you go to, I'm going to log in. So do you have access to a webcam or a phone or something?
I have a phone, but that's where I only have the phone. I don't have a second webcam.
Do you have can you get access to a webcam that you can stick on your computer?
Potentially, but it might be easier just to find one in person, and that's where I'm trying to weigh the odds
Okay.
out here.
Okay.
Scott, could he maybe use a significant other's phone or a friend's?
You can use anything
So they
you
have
want.
two phones?
I mean, the exam still has to be taken on a computer. So there's no way around that. But you know, the secondary device can be any phone or anything that has a camera. So if we go to the ARRL and exams, let's see. Find an amateur radio license exam in your area. Give me a zip code.
85226.
I think you have choices.
Holy cow. Okay, I didn't know that this was an option. I've been going to individual ham sites, and it's kind of a runaround.
Yeah. Yeah, you have choices. I would say call and make sure they're doing it, but yeah, there are many choices.
Fantastic. Hey, thanks for your help with this, and thanks again for the class. I really appreciate it.
Yep. And I got to go and join a group of examiners. Any other questions?
Well, to just echo what everybody else is saying, thank you very much.
Well, thank you all for spending your weekend with me.
Thank you.
All right. Thanks all. Good luck on those tests.
Thank you. Good luck, everybody.